The Earth has been destroyed more than once, 90% or more of every species alive, erased in a single event across an interval that geologists describe as brief and that you would describe as instant. At least 5 such events are attested in the planet's known biography. Probably there were more. Each time, something small was not quite killed. Something dispersed, unspecialized, and lucky enough to have been in a burrow or a pond or under a stone when the worst of the killing happened. You are here because that run of luck held. Tonight is about the 5th of those events, the most recent and the shortest. It ended with 66 million years of mammalian inheritance on the other side of it, and began with the sky catching fire. For about an hour on a spring afternoon, anywhere on the Earth where you might have been standing, the Cretaceous equator, the Cretaceous Arctic, the middle of what is now the Pacific, the sky above you glowed in a way that had nothing to do with sunlight. The air itself was luminous. Vegetation began to smoke. The ground reached the temperature of an oven set for slow roasting, and anything dry enough to catch caught. This did not come from a second sun. It came from a small rock. The rock was about 10 kilometers across, wider than Everest is tall, but not enormously so. It hit the shallow sea that covered what is now the Yucatán Peninsula at around 20 kilometers per second. That speed matters. At that speed, a collision is not mechanical the way a car crash is mechanical. The kinetic energy does not crumple metal. It vaporizes rock. A column of earth several kilometers tall went from solid limestone to incandescent gas in less than a minute. Most of that gas did not stay down. Some of it traveled up, past the atmosphere, into ballistic space, and back down again, everywhere on Earth, within a few hours. That second fall was the fire. Each small piece of re-entering ejector arriving at hypervelocity behaved like a tiny incoming spacecraft, dumping its kinetic energy into the surrounding air as heat. Multiply by billions of small pieces, arriving simultaneously in the upper atmosphere across the entire planet, and you have an infrared pulse of roughly 10 kilowatts per square meter at ground level. That is the intensity of an oven. For a few minutes, the entire sky, everywhere on the planet, was the heating element in that oven, and everything below it was what was being cooked. Most of the animals that did not have a hole to get into or a body of water to get under died in that first hour. Forests burned. Large exposed animals, the ones too big to hide, began to overheat or to run or simply to stop working. The rest of the story follows from that single afternoon. The 100,000 years of winter, the 10 million years of recovery, the 66 million years during which a specific kind of small, burrowing, unspecialized creature kept its grip on the planet long enough to become, eventually, you, all of that began on an afternoon that, 10 minutes before the sky caught fire, would have seemed entirely ordinary. If this sounds worth being made, the subscribe button is how a channel like this keeps breathing. And something I've been curious about. When you think about deep time, about how many times the planet has done something like this, and how thin the line has always been, does the scale make you anxious, or does it make you calm? I read the answers, and I find that question more useful than most of the data in this field. Now, if you're comfortable, get slightly more comfortable. The lamp nearest you is probably brighter than it needs to be. Your shoulders are probably tighter than they need to be. The Yucatán coast, on the morning before the sky caught fire, was also bright in a way nothing about it was yet showing. The air was warm and a little humid. The sea was shallow and the color of blue-green glass. It was an ordinary spring morning in the Cretaceous, and nothing about it was wrong. The rock was about 9 minutes away. The coast that would later be called Yucatán was, that morning, about 20 degrees north of the Cretaceous equator, warm enough all year that the difference between seasons was felt mostly as a change in the rain. It was spring in the northern hemisphere, We know this now from the growth bands in fish bones that were buried later the same day, 3,000 kilometers away, and from the pollen timing in sediments preserved underneath a layer of ash. But for the animals on the coast, there was no particular reason to mark it as a boundary. The rainy season had begun. The inland rivers were running a little higher than they had been in winter. The coastal forest was in the slightly brighter green of new growth, and the first flowering magnolias were open in the understory. The shoreline ran roughly east to west, which meant the sun came up over the Tethys waters to the right of anyone standing on the beach facing north. The sea was shallow, a carbonate platform extending offshore for tens of kilometers, the kind of turquoise-green shelf water that looks almost luminous from above because the sunlight reaches the white limestone floor and comes back up through the water column cleanly. Ammonites drifted in that water. Not many this late in the Cretaceous, but enough that a single long walk at low tide would have turned up the shells of the dead and, more rarely, the living. A coiled creature the size of a dinner plate, or occasionally larger, drifting with its tentacles downward, gently hunting. They had been doing a version of this for about 300 million years. Some of the lineages on that coast that morning were older than the dinosaurs themselves. A large duck-billed dinosaur, something in the hadrosaur family, the most common herbivores of the late Cretaceous, was almost certainly somewhere along that beach, browsing on the coastal vegetation. Hadrosaurs travelled in groups, laid eggs in communal nesting grounds, and had among the most sophisticated chewing apparatuses of any land animal before or since, dental batteries of hundreds of teeth, self-sharpening, capable of grinding fibrous plant material the way a mill grinds grain. They were not a lineage in trouble. The fossil record across the final million years of the Cretaceous, read carefully, shows hadrosaurs diversifying. New species appearing in new basins, body sizes filling out new ecological roles. The same was true of the horned ceratopsians, the dome-headed pachycephalosaurs, the small feathered theropods that are the closest relatives of birds, and the tyrannosaurs that ate them. This is worth pausing on because the popular version of the story usually says something else. The popular version says the dinosaurs were already dying, that the impact only finished what climate and competition had begun, and that the end of the Cretaceous was a kind of assisted suicide dressed up as a disaster. That story has been circulating in some form since the 1960s, and it keeps coming back because it feels more satisfying than the alternative, which is that the dinosaurs, as an ecological group, were doing fine and an accident killed them. The careful work of the last decade has made this clear in several different ways. Ecological niche modelling, tested against the terminal Cretaceous fossil record, finds no climatic signal predicting decline. Bayesian phylogenetic analyses looking for slowdowns in speciation rate find none that are statistically robust. Region by region, North America, Europe, Asia, the terminal Cretaceous faunas look like healthy, diverse ecosystems. Some dinosaur lineages were contracting, others were expanding. On the whole, the clade was generating new species as fast as it was losing old ones. What killed them was not momentum. What killed them was a 60-degree trajectory that had been established about 4 billion years earlier, when their eventual executioner formed out of the same dust as the Earth itself, and set off on an orbit that would, eventually, cross the one Earth was on. So, if you had been standing on that beach, and if you had been able to stand, which no primate was yet capable of, the ancestors of primates on that day being no larger than a mouse, you would not have seen anything wrong. The sea would have looked the way shallow tropical seas look today. The forest behind you would have sounded the way a dense forest sounds in spring, with birds and insects and the low rumble somewhere in the distance of a hadrosaur calling to its group through an elongated, resonating cranial crest. The air would have smelled of salt and wet limestone and flowers. You would have had no reason to think of the sky as anything other than the usual thin blue shell above it all. High in that shell, around 9 minutes before the end of this world, a white point appeared. It was nothing much to look at, visible only because of the sun angle, a small, bright dot moving slowly, the way a high-altitude aircraft moves across the sky on a clear afternoon. No sound yet, no heat yet. Just a point of light, slightly brighter than Venus at its most brilliant, crossing the zenith on a path that led southwest. None of the animals on the beach looked up. There was no reason to. Bright points moving in the sky were not yet, in 66 million years of vertebrate life on land, a category of thing that mattered. Birds looked at the sky for predators, and the predators in the sky were other birds. Insects had evolved pattern recognition for silhouettes and movement at close range. The hadrosaur, the ammonite, the Mesozoic mouse and everything else around them were operating on a fully functional, beautifully tuned model of what mattered in their world. The model did not include the possibility of a 10-kilometer rock arriving from somewhere outside it. And so the morning continued in a perfectly ordinary way for the next 9 minutes. The light in the sky got a little brighter still. The small things in the forest, sensitive to movement, began to quiet, though none of them had the vocabulary for what they were responding to. The hadrosaur paused in its browsing. An ammonite, in shallow water, contracted briefly, then resumed drifting. Whatever instinct was stirring had no clear shape yet. It would not acquire one until the thing in the sky was close enough to be felt. Then, in the last 30 seconds, the air itself began to warm. Not the usual warmth of a spring morning, a dry, radiant heat coming from directly overhead, of a kind none of these animals had an ancestor who had ever experienced, because no ancestor of any of them had ever lived through a moment like this. The rock was no longer a point in the sky. It was the sky. The rock arrived on a line that came in from the northeast at an angle between 45 and 60 degrees off the horizontal, which is to say it was falling steeply but not straight down. This angle mattered more than any other single parameter of the impact, and it is worth understanding why before going any further, because almost everything that followed, the global fires, the darkening, the winter, the 96% marine extinction, the specific 3/4 of terrestrial species that vanished, depended on that angle more sensitively than it depended on the size of the rock itself. A rock arriving vertically would have dug the deepest hole, but released the least climate-altering gas, because the column of vaporized material would have gone almost straight up through the thinnest possible cross-section of atmosphere and come back down more or less where it started. A rock arriving very shallowly, at 20 degrees or less, would have skipped and grazed and spent most of its kinetic energy heating the atmosphere rather than the crust, and the crater it left would have been a long gouge rather than a deep bowl. Between those extremes is a sweet spot, roughly 45 to 60 degrees, at which the amount of target rock vaporized is maximized. The height of the vapor column is maximized, and therefore the amount of sulfur, carbon and dust injected high into the upper atmosphere is maximized. The angle the rock actually arrived at was inside that sweet spot. When researchers at Imperial College London modelled this in 3 dimensions in 2020, running the numbers through the asymmetries preserved in the crater's subsurface structure, they called it the worst-case geometry. A vertical impact would have made a bigger hole and less mass extinction. A glancing one would have made a smaller mess and more survivors. What actually happened was the configuration that produced the most climate-active gas per kilogram of impactor. And it happened because of a trajectory established billions of years earlier, when whatever gravitational nudge sent this particular chunk of chondritic rock onto its final orbit happened to do so at exactly the wrong inclination for the world about to become its target. The rock was, by cosmic standards, small. 10 kilometers is about the width of Manhattan. If you placed it on the ground intact, its summit would be higher than Everest. But most asteroids in the solar system are smaller than that, and larger ones exist. What made this one matter was not its size. What made it matter was where it hit and how fast. It hit at roughly 20 kilometers per second. This is a speed that has no useful analog in ordinary human experience. A rifle bullet travels at something under 1 kilometer per second, a high-velocity anti-tank round at about 1.5. The rock was moving at 13 times that, and carrying with it the gravitational acceleration it had accumulated on its long fall into Earth's well. At that velocity, collision is not really a mechanical event in the usual sense. The atoms in the front of the rock and the atoms in the top of the seafloor have, in effect, no time to respond to each other's arrival before the pressure wave behind them has already turned them into plasma. Kinetic energy cannot be stored elastically at those speeds. It is dumped as heat, and the heat is enough to vaporize stone. What follows is a sequence of events that can be resolved second by second from the rock record itself. In 2016, a joint drilling expedition of the International Ocean Discovery Program and the International Continental Scientific Drilling Program put a single borehole down into the peak ring of the buried crater offshore from the Yucatán coast and brought up an unbroken core of rock that captured the entire first day of the Cenozoic in stratigraphic order. The bottom of that core is impact melt, liquefied basement granite, cooled in place. Above that, a layer of breccia, shattered rock reassembled in chaotic fragments. Above that, a finer-grained breccia sorted by flowing water. Above that, a thin dusting that reads as tsunami deposit, with charcoal mixed in. And above all of it, less than a meter of ordinary ocean sediment separating the first day of the New World from the second. 130 meters of rock deposited in something like 24 hours, recovered 500 meters below the modern seafloor by a drill crew working on a lift boat named the Myrtle. What that core tells you, when you read it carefully, is the following. In the first second, the rock made contact with the water column over the Yucatán shelf. The water was about 100 meters deep at the point of impact. That water had essentially no role in slowing the rock. The energy of the collision was large enough that the ocean above the target was, for the purpose of the physics, negligible. The rock passed through it as if it were not there, vaporizing a cylinder of seawater about as wide as the rock itself in roughly 1/100th of a second, and then struck the carbonate platform beneath. Within the next several seconds, the rock drove itself and a substantial volume of the seafloor downward and outward. The shock wave moving ahead of the rock compressed the target rock to pressures exceeding 500 gigapascals, 100,000 times atmospheric pressure at sea level. And the materials on either side of that shock front reached temperatures of tens of thousands of degrees. A transient crater opened, a bowl about 100 kilometers across and 30 kilometers deep, briefly deeper than the atmosphere is tall. The rock itself ceased to exist as a coherent object somewhere in those first several seconds. It did not explode, exactly. The word does not apply. It was absorbed into the plasma it had created. Its atoms mixed into the vapor of the granite and limestone and anhydrite it had struck. The transient crater was not stable. A hole that size and shape, carved briefly into a planet's crust, cannot stand. In the next minute, its walls collapsed inward under their own weight. The floor rebounded upward the way the surface of a pond rebounds after a stone has dropped into it, and an inner ring of crystalline basement rock, material that, before the impact, had been sitting quietly about 10 kilometers below the seafloor, got lifted into a circle of hills several hundred meters high, arranged in a ring about 140 kilometers across. This is the structure the drillers in 2016 were after. It is called a peak ring. Peak rings form in the largest impact craters in the solar system, on the Moon and Mercury and Mars, and until the Yucatán drilling, there had been a long-running argument about which rocks actually make up such a ring, whether they come from the deep basement, forced upward, or from the surface, collapsed inward. The core resolved the argument. The rocks in the Chicxulub peak ring are deep basement, lifted from below, and they got there in under a minute. In the same minute, a plume of vaporized seafloor and impactor, thousands of gigatons of it, launched upward and outward, faster than Earth's escape velocity. Some of it left the planet entirely. Most of it did not, but it reached altitudes high enough to sit above the atmosphere for the better part of an hour on ballistic trajectories that would take it halfway around the world and back. That plume carried the carbon dioxide from the vaporized limestone. It carried the sulfur from the vaporized anhydrite. It carried pulverized silicate dust, fine enough that the smallest particles would stay airborne for years once they finished falling. And it carried, mixed through all of it, the atoms that had once been the rock, the iridium and the platinum group metals and the other signatures that much later would settle globally as a thin clay layer and would, 80-some million years later still, allow a father and son in a California laboratory to figure out what had happened. By the end of the first minute, the shape of what comes next was already set. The crater was closing up. The plume was rising. The tsunami was beginning to move. And the atmosphere of the entire planet, not just over the impact site, but everywhere, was about to receive a delivery. In museum drawers in several countries, there is a thin black line. It sits inside hand-sized pieces of rock, sandwiched between paler stone above and below, and it is rarely more than 1 or 2 centimeters across. In Gubbio, in the Italian Apennines, it runs through a creamy pink limestone that was once a deep seafloor. At Stevens Klint in Denmark, it is the reason the cliff has a distinctive black band visible from a kilometer offshore. In North Dakota, in the Hell Creek Formation, it sits at the top of a muddy sandstone unit that had been, until that moment, an ordinary late Cretaceous floodplain. Across the planet, on every continent where sedimentary rocks of the right age have been exposed, geologists find the same thin layer, not approximately the same layer, deposited to within the precision anyone has been able to measure simultaneously. What the layer is made of varies a little from site to site because the conditions at each site varied. But the core ingredients are consistent. It contains, in concentrations far above anything expected in ordinary terrestrial rock, iridium, a platinum group metal abundant in certain kinds of asteroid and vanishingly rare at Earth's surface. It contains small glass beads called spherules that are chemically identical to melted and quenched terrestrial rock. It contains grains of shocked quartz, identifiable under a microscope by the parallel lamellae running across them, which can only form under pressures that no volcano can produce, and it contains soot, a lot of soot, enough at several sites that the total carbon in the global layer, if you tally it up and extrapolate across the Earth's surface, is comparable to the entire standing biomass of the terminal Cretaceous forests. That is what the record says. Now the question, and it has been one of the genuinely productive arguments of the last 40 years of Earth science, is what the record means. Start with what is not in dispute. The ejector plume that went up from the impact site, in the minute or so described already, reached altitudes well above the atmosphere. Most of it was not traveling fast enough to escape Earth's gravity entirely. So, it came back down. The timing of its return depended on how fast a given piece of ejector had been launched and at what angle. The fastest material travelled halfway around the world before it re-entered, while slower material came down closer to the impact site. The return, when it happened, was not gentle. Each spherule, each droplet of molten rock that had cooled and solidified somewhere in ballistic space, re-entered the atmosphere at several kilometers per second. Friction with the air heated it back up to incandescence. Imagine, in the thinness of the upper atmosphere, a shower of glowing droplets arriving across an entire hemisphere of sky. Now, imagine it happening everywhere at once. The cumulative infrared radiation from that shower integrated across the sky and aimed downward toward the surface of the Earth is the thermal pulse. The models that attempt to quantify this pulse have been getting better for decades. The original calculations from the early 90s suggested a flux of somewhere around 10 kilowatts per square meter at ground level, sustained for tens of minutes, enough, in principle, to ignite dry vegetation across the entire planet. This was the picture that motivated a hypothesis known as the global firestorm, that in the hours after impact, every forest on Earth caught fire simultaneously, and the soot in the boundary layer is the ash of a burning biosphere. It is a dramatic hypothesis. It explains the selectivity of the extinction nicely. The survivors are almost all species that could have taken shelter from heat and fire underground or in water, while the losers are almost all species that could not. And the soot in the boundary clay does need an explanation. Later modelling has complicated the picture rather than overturning it. When you include the opacity of the spherule shower itself, the fact that as more and more spherules arrive, the accumulating cloud of them starts to absorb and scatter the radiation coming from above. The flux at the ground drops significantly and the duration shortens. By the most detailed calculations to date, the peak thermal pulse at the surface probably reached around 5 to 15 kilowatts per square meter, but only for a few minutes at peak intensity, not tens of minutes. That is still an extraordinary amount of heat. 5 kilowatts per square meter is the setting you would use to broil food in an oven. 15 is closer to the surface of a cooking element. The sky was doing that briefly across large portions of the planet. But briefly is doing some work in that sentence. A pulse of a few minutes is not clearly enough by itself to ignite mature wood in a damp forest. Dry grass, yes. Leaf litter, yes. Anything with a high surface-to-volume ratio, yes. Standing trees, probably only if they were already stressed or already burning from something else. Experimental work has confirmed the intuition. When researchers actually took samples of dry and fresh Cretaceous-style vegetation, ferns, cycad fronds, conifer needles, and exposed them to radiant heat fluxes comparable to the modelled pulse, the dry material ignited readily. The fresh material mostly did not, or only charred superficially. This has led some researchers to propose that the fires were real but patchy, concentrated in dry landscapes and in areas closer to the impact, rather than forming a truly global simultaneous firestorm. Others have pointed to a second source of soot that does not require surface ignition at all. The target rock at the impact site itself was rich in organic carbon-bearing sediments, and a great deal of that organic material would have been vaporized and pyrolyzed in the fireball and then lofted into the upper atmosphere directly, producing soot without any forest needing to have burned. That soot, arriving in the stratosphere, would have behaved identically to soot from global fires and would have contributed to everything that followed. The honest answer about the firestorm, then, is this. There was a thermal pulse, and it was severe. There were fires, very probably large and widespread fires, especially in landscapes that were already dry. Whether every forest on the planet burned simultaneously in the first few hours is still uncertain and may never be definitively resolved. The soot in the boundary layer has at least 2 plausible sources, and both probably contributed. What is not in dispute is that for a period of minutes to hours, the sky across most of the Earth glowed brightly enough and hot enough that any animal caught in the open and unable to take shelter faced conditions its body could not handle. One data point sharpens the picture considerably, and it comes from a place very far from the impact. Among the sediments drilled from the Chicxulub Peak Ring, in the top of the 130-meter first-day deposit, there is charcoal. Not a lot of it, but enough. And the charcoal is mixed into a layer interpreted as tsunami deposit, material that washed back into the crater from distant shorelines within the first day, carrying with it the debris of whatever those shorelines had just been through. For charcoal to have reached the crater by that route, something on the shorelines, within the tsunami's reach, had to have burned. The burn had to have happened quickly, within hours of impact. And the landscapes the tsunami drew from stretched for at least 1,000 kilometers around the Gulf of Mexico. Somewhere within that radius, forests or prairies were burning before the ocean came back and swept their remains into the crater. Whether the same was happening at the same moment in Asia or in Antarctica or on the western coast of what is now North America, that is harder to say. The soot is global. The fires that produced it may not have been. What is clear is that the atmosphere in the hours after impact was not merely warming. It was filling with dust, with soot, with aerosols still forming out of the sulfur that had been carried up in the plume. The next several hours would complete the delivery. By the time the sky cooled enough to stop glowing, it would no longer be transparent either. The rock that had hit 9 minutes before noon on a Cretaceous spring day was no longer anywhere. Its atoms were spread across the upper atmosphere of the Earth. Over the next several days, they would begin their slow fall, some as fine dust, some as the iridium-rich fallout that would eventually land on the seafloor at Gubbio, some as the spherules that, 3,000 kilometers to the north, would find their way into the gills of a fish that was, at that moment, still alive. 3,000 kilometers to the north of the impact, in a meandering river channel that drained into an inland sea, a sturgeon was feeding. The river, in what is now southwestern North Dakota, cut through a subtropical floodplain at the eastern edge of a great shallow waterway geologists call the Western Interior Seaway. That seaway ran from the Gulf of Mexico up through the middle of the continent and all the way to the Arctic, splitting the future North America into 2 long islands. The water was quiet. The river carried its usual load of sand and silt and organic debris from the forests upstream. Along the bank, dinosaurs had left tracks in the damp mud only hours before. Hadrosaurs, small theropods, the occasional larger footprint. A leatherback-style sea turtle drifted in a quiet bend. The ammonites that lived in the seaway were present in some numbers, their coiled shells occasionally washing up on the inland shoreline after a storm. The forest beyond the riverbank was dense with conifers and early flowering plants, and the insects in it on that particular morning were doing what insects do on a warm spring day. The sturgeon itself was roughly 1 meter long. It was an ancestral form of a lineage that still exists, a group of bony fish with armoured scutes running down their sides and an underslung shovel-shaped snout used for foraging along the bottom. The fish was alive in a way that the scientific record, which ordinarily preserves only bones, rarely captures. The growth rings in its fin rays recorded its age, about 3 or 4 years, and the chemistry of those rings recorded the seasons it had lived through. Its last set of rings, laid down in the months before this morning, showed the isotopic signature of spring feeding, plankton blooms, warming water, the recovery of activity after winter. It had been eating well. None of this should have been recoverable. A single fish dying on a particular day, on a particular river, 3,000 kilometers from an impact site, leaves no fossil if nothing unusual happens to preserve it. What happened on this river was unusual. The seismic wave from the impact reached the area in a little over 13 minutes. By the time it arrived, the site had already been going through something that would have been, if any living thing there had been capable of noticing, distinctly wrong. The air had darkened without a cloud front having arrived. The horizon to the south had a light at it that did not correspond to any hour of the morning. But neither the sturgeon nor the animals on the bank had the perceptual equipment to make anything of these changes, which were mild so far and slow. What did get everyone's attention was the ground. A magnitude in the upper tens for earthquake intensity is not really an earthquake in the way the word is usually used. It is a global event, a pulse of energy moving outward from a single point at several kilometers per second through rock, which arrives at 3,000 kilometers distance as a prolonged shaking that lasts several minutes and displaces the surface by tens of centimeters in each direction. The river responded the way any standing or slow-moving body of water responds to an earthquake. Its surface oscillated, large waves formed and collapsed back into themselves, and water that had been in one part of the channel sloshed violently into another part. The phenomenon has a name. It is called a seiche, and it is the same physics that makes the water in a swimming pool heave from end to end during a distant quake. What made this seiche unusual was its amplitude. The waves in the river that morning were not centimeters tall. They were meters. The sturgeon was caught in the turbulence. Fish can handle moving water, sturgeon especially, which live in currents, but they cannot handle water that is suddenly trying to go in several directions at once, and they cannot handle being slammed repeatedly against their own riverbed. The fish was bruised, disoriented, and pushed into a zone of the channel where the water was thick with suspended sediment. It continued, for the moment, to breathe. Then, beginning perhaps 15 minutes after the impact and continuing for the next hour or two, a second and stranger thing began to happen. From the darkening sky above the river, small objects started to fall. Spherules, droplets of molten rock from the Yucatán, launched into ballistic space at the moment of impact, cooled into glass beads during their flight, and now re-entering the atmosphere at the latitude of North Dakota after a journey of about 40 minutes. Some were no larger than a grain of sand. Some were the size of a pea. They arrived individually at first, then in increasing numbers, and for a time the air over the river was full of them, the way the air over a river is sometimes full of pollen in a hard spring wind, except that these grains were hot and glassy and had until recently been part of the seafloor of the Gulf of Mexico. The sturgeon, still breathing, still moving water across its gills, inhaled them. The spherules lodged in the gill filaments, where they remained. Some of the fish around it did the same. Crucially, and this is one of the key data points the site has yielded, not all the fish caught spherules because not all of them were still breathing by the time the spherules arrived. Some had already died in the seiche. Those fish had their mouths closed. The ones that breathed in spherules were the ones that were still alive when the spherules were falling. The difference between those two populations, preserved in the rock, is how paleontologists have been able to reconstruct the order and timing of events. Within another hour or two, the river buried everything. The seiche, continuing, stirred up the floodplain sediment and deposited it in a thick, chaotic surge layer over the dead and dying fish, the drowned logs, the occasional dinosaur carcass that had been caught by a wave at the edge of a channel. Ordinarily, organic matter in such a setting would decay on a timescale of weeks to years. In this case, the sediment arrived fast enough and deep enough to entomb the remains almost immediately. A few tens of centimeters of mud became a meter of mud, then more, as the seiche worked the river for hours. By the time the water settled and the sky darkened further toward genuine night, the deposit was sealed. What had been, for a brief interval, a record of living animals caught in a catastrophe had become a rock in progress. This site is called Tanis. It sits in the Hell Creek Formation, which has been one of the most intensively studied terminal Cretaceous rock sequences in the world for a century. The site itself was identified in 2008 by a paleontologist named Robert De Palma, who has been its principal excavator ever since. In 2019, De Palma and his colleagues published in the Proceedings of the National Academy of Sciences their interpretation of Tanis as an impact-triggered seiche deposit capturing the first hour or so of the day. The paper drew enormous attention. It also drew pointed scrutiny because some of the broader claims De Palma's group has since made about the site regarding mummified dinosaur skin, a possible pterosaur embryo, and a fragment of the impactor itself have not been uniformly replicated or accepted by other specialists, and De Palma's own public profile has occasionally been described in terms that make some colleagues uneasy. The 2019 seiche interpretation is, as of now, considered robust by most of the community. The further claims sit in different positions along a spectrum of acceptance. One finding in particular has been confirmed independently and confirmed with a precision that settles a long-standing question. In 2022, a team led by Melanie During, working separately from De Palma's group, analysed the growth patterns and isotopic chemistry of fish bones from the same Tanis beds and published the result in Nature. The fish had died in the boreal spring, in the northern hemisphere's March, April or May, not in summer, not in autumn, spring. The growth signatures in the bones were unambiguous, and they matched in the sturgeon and in the paddlefish and in the other aquatic species they examined. The impact that ended the Mesozoic had happened at a specific season, in a specific hemisphere, and that season was spring in the north. This fact matters for more than its precision. Spring is the moment when northern hemisphere ecosystems are emerging from winter dormancy, when animals are beginning to reproduce, when plants are putting out new growth, when insects are hatching, when the biological machinery of an entire hemisphere is shifting from quiescence to activity. An impact in that season catches organisms at their most exposed: eggs in the nest, buds on the branch, larvae in the shallows. An impact in the northern autumn would have hit just as many ecosystems were preparing for winter, storing energy, withdrawing. The fact that this impact hit in the northern spring may be part of the reason the northern hemisphere was harder hit than the southern one in some of the patterns that emerge in the fossil record over the next several million years. The season is not incidental to the extinction, it is part of its geometry. The sturgeon in the river did not live long enough to have a view on any of this. It died in the surge, probably within 2 or 3 hours of the impact, with a mouthful of water and a gill raker full of glass beads that had, a little more than half an hour before, been part of a seafloor 2,000 miles to the south. The fish was buried, sealed, and left in the sediment for 66 million years, while continents rearranged themselves above it, and the Hell Creek floodplain became the dry, eroded badlands it is now. It was excavated in the first decades of the 21st century by researchers who could read from its bones both the season of its death and, in the spherules lodged in its gills, the distance in minutes between its last breath and an event that had already changed everything. The spherules themselves were still arriving at that point over much of the rest of the planet. Fires were burning in some places and not in others. The sky was not yet dark, exactly, but it was no longer clear. In the upper atmosphere, the first of the dust was beginning to organize itself into the layer that would, for the next decade and a half, quietly change the amount of sunlight that reached the surface. A particle of silicate dust, a few micrometers across, does not fall through air the way a rock falls through air. It falls so slowly that for any practical purpose, it is not really falling. Air is a fluid, and a fluid pushes back on anything trying to move through it, and the ratio of the pushing back to the downward pull of gravity depends on how much surface the particle presents relative to its mass. For a pebble or a grain of sand, gravity wins by an enormous margin, and the particle arrives at the ground in seconds. For a particle small enough, the two forces come into approximate balance, and the particle settles at a rate measured not in seconds, but in months or years. A 1-micrometer silicate grain released into the stratosphere at an altitude of 30 kilometers takes, by the best current estimates, somewhere between a decade and a half to reach the surface under its own weight. That is not a failure of the physics. That is how the physics works at that size, and it is the single most important fact about what happened after the sky stopped burning. In the hours following the impact, the plume that had risen from the Yucatán dispersed. The coarser ejecta, the centimeter-scale chunks, the spherules, fell back out on timescales of minutes to hours, and they were what produced the thermal pulse already described. The finer material did not fall back out. It stayed up. Some of it had been lofted to altitudes well above the weather-producing layer of the atmosphere, into the stratosphere, where there is almost no vertical mixing and where the horizontal winds, moving around the planet, spread any material injected into them into a thin global veil within a few weeks. Within about a month of the impact, the entire stratosphere of the Earth was carrying a load of fine silicate dust and a separate load of sulfate aerosol that had formed out of the sulfur vaporized from the anhydrite layers at the impact site. Both populations of particles were small, both were good at scattering sunlight, and both were going to be in the atmosphere for a long time. The consequence, at the surface, was darkness. Not total darkness. The sun continued to rise and set in the usual places, but the amount of sunlight reaching the ground on any given day was reduced by a factor that climate modelers have estimated variously, and the estimates have moved around over the last decade. The older models, working from a scenario dominated by sulfate aerosols, produced reductions of 80% or more in the first year, recovering slowly over the following decade. More recent models, paying closer attention to the fine silicate dust and giving it a longer atmospheric lifetime, suggest a reduction of similar severity, but potentially stretching over a longer period, something like 12 to 15 years before solar transmission returned fully to its pre-impact baseline. The exact numbers depend on what you assume about particle size distributions and chemical aging processes, and the science has been actively revising itself even within the last 3 years. What is consistent across all the models, and what the sedimentary record confirms, is that for the better part of a decade, the Earth received substantially less sunlight than it had before, and at the peak of the darkening, it may have received as little as 1/5 of its usual solar flux. This is a difficult thing to convey at scale because sunlight is not something most people consciously measure. But the consequence of removing most of it across the entire planet cascades through every system that depends on it, and those systems include essentially all of them. A comparison that is frequently used and that is useful even if it is imperfect is the eruption of Mount Pinatubo in 1991. Pinatubo put a relatively small amount of sulfur dioxide into the stratosphere, about 17 million tons, and that sulfur, converting to aerosol over the following weeks, caused a measurable cooling of the global climate by roughly 0.5 degrees Celsius for about 2 years. The event was large enough to be detectable in weather records worldwide, to reduce crop yields in some regions, and to delay the seasonal warming for a couple of summers in ways that meteorologists could track in detail. Pinatubo was, in terms of sulfur mass loaded into the stratosphere, somewhere around 1/10 to 100th of what Chicxulub did. The sulfate component of the impact's load was something like 1 to 2 orders of magnitude larger than Pinatubo's, and the sulfate component was only part of the total load. It may not even have been the dominant part, according to the most recent work, once fine silicate dust is properly accounted for. So the right way to picture it, as an order of magnitude, is this. Imagine the Pinatubo cooling. Now imagine that cooling not as a half-degree drop for 2 years, but as a 10 to 20 degree drop sustained over most of the planet for years on end. That is the low-end version of the impact winter. The high-end versions, which some of the older modelling produced, had tropical oceans cooling by 6 or 7 degrees and mid-latitude continents briefly freezing in summer, with temperatures at higher latitudes dropping by numbers that stop being meaningful in everyday terms, 20-25 degrees. The more recent modelling has softened some of these extremes, but the qualitative picture is unchanged. The planet got cold. It stayed cold for longer than any ecosystem existing at the time had any ability to wait out. And the cold was not the worst of it. The cold came with the darkness, and the darkness was, in its own quiet way, the actual executioner. Photosynthesis requires light, not a little light, a threshold amount of light below which the chemistry that turns carbon dioxide and water into sugar simply stops working. Plants have evolved an enormous variety of strategies to deal with low light: larger leaves, darker pigments, shade-tolerant chloroplast arrangements, slowed metabolism. But those strategies all assume some sunlight is available. In the first year after the impact, across much of the planet, the amount of sunlight was below the compensation point for most terrestrial plants. That means the plants were, metabolically, losing more carbon than they were gaining. They were eating themselves, at rates governed by how much stored energy they had, and once that energy was used up, they died. Small plants, annuals, ground cover, died first. Trees, which have large reserves in their woody tissues, lasted longer. But even trees have limits. Once a tree has exhausted its stored carbohydrate and cannot photosynthesize new carbon, it will drop its leaves, shut down its living cambium, and die standing. In the paleobotanical record from the first centuries after the impact, this is what is found: intact standing dead forests, slowly toppling. And in between, a particular organism came into enormous temporary abundance because it did not need sunlight to reproduce. It needed only spores and moisture. That organism was fern. The so-called fern spike, visible in sedimentary layers at many sites worldwide just above the boundary clay, is one of the clearest signals in the terrestrial record. Where the pre-impact vegetation was a rich mixture of conifers, flowering plants, cycads, and ferns in roughly balanced proportions, the immediate post-impact layer is, at many sites, almost pure fern spores. For a period of years to decades, the land surface in many places was effectively a global fern prairie. Ferns reproduce from spores that can remain dormant in soil, and a fern spore that germinates needs far less initial light and no animal pollinator, which made them essentially the only vascular plant group positioned to take over bare or dying ground in that light environment. The fern spike is not a sign of health. It is a sign of having lost almost everything and being left with what grew back first. In the oceans, the equivalent collapse was happening at the base of the food chain. The organisms that do most of the photosynthesis in the sea are microscopic: diatoms, coccolithophorids, dinoflagellates, cyanobacteria. Some of these produce shells of calcium carbonate, the coccolithophorids, and their fossilized shells, accumulating on the seafloor, build the limestone of which entire continental shelves are made. In the boundary interval, the accumulation of these shells stops almost completely. The surface ocean, deprived of light, simply ceased to produce most of its primary biomass. The shells that were there already sank, and the sinking continued for a while as the existing populations died off. Then the rain of shells ran out, and the seafloor began accumulating, instead of fine carbonate ooze, a barren clay. The same clay, in fact, that contains the iridium. The boundary clay marks, among other things, the interval during which the ocean above it briefly stopped making the raw material for marine sediment. This is what had to happen for the rest of the extinction to make sense. The dinosaurs and the ammonites and the marine reptiles and the vast majority of larger animals that died did not die in the fire, although some did. They did not die in the ground shaking, although some did. They died because the food died. And the food died because the light died. And the light died because a decade or more of fine dust and sulfate aerosols, lofted by the impact, sat in the upper atmosphere and refused to fall out on any timescale a Cretaceous ecosystem could survive. The dark, when it arrived, was not sudden. In most places, the thermal pulse faded within hours, and over the following days, the sky took on a strange, uniform haze. Not a cloud front, not a smoke plume, but the aggregate of an atmosphere that had stopped being fully transparent. Over weeks, the haze thickened. Over months, the daily high temperature fell and kept falling. And over years, what had been the end of the Cretaceous became something else. A planet in a configuration it had not been in for hundreds of millions of years, if ever. The plants that had been the base of the terrestrial food chain were gone. The plankton that had been the base of the marine food chain were gone. What remained on land and in the sea was a starving system holding its breath and waiting to see what, if anything, was coming back. The temperature, meanwhile, was about to take its own turn. On an afternoon in what should have been July, about 18 months after the impact, in a bend of a river in what is now eastern Montana, there was a thin skin of ice along the shaded edges of the water. The ice was no thicker than a fingernail, and it was not continuous. It formed where the river had slowed into backwaters and where trees, still standing but leafless, cast shadows that had not lifted all day. Elsewhere the river ran free. But the ice was there. It formed every clear night now, and on the cold afternoons it refused to melt before the next nightfall, and a Cretaceous ecosystem that had never, in any of its 100-million-year history, seen ice on its summer rivers was being asked to deal with it. If you had been standing on that bank, and if your mammalian ancestor on that bank, about the size of your thumb, had been able to form the thought, you would have noticed that the usual summer sounds were mostly gone. No chorus of insects, no calls of the great reptiles that, before all this, would have been audible from several kilometers in every direction. The sound of the river itself was the loudest thing, and even that sounded wrong, because the water was carrying less of what usually made it noisy. Fewer leaves, fewer branches, no carcasses moving downstream, nothing living in the shallows, making the small splashing noises that summers had always contained. The sun, when it broke through the haze, felt weak on the skin. The haze itself did not look quite like a cloud layer, did not move quite like a cloud layer, and did not disperse at the end of the day the way ordinary weather dispersed. It was simply there, reducing the light, and it had been there for over a year. The event that the analogy most readily reaches for is the one that happened in 1815, when the volcano Tambora on the Indonesian island of Sumbawa erupted. Tambora put enough sulfur into the stratosphere to cool the global climate by about a degree for the following year, and the year that followed it, 1816, became known in Europe and North America as the year without a summer. Snow fell in Quebec in June. Frost killed crops in New England in July and August. The Indian monsoon failed. The subsequent famines in Yunnan and in parts of Europe killed an uncertain but substantial number of people. Tambora was, in historical terms, the largest eruption humans have directly recorded, and its effects on global climate were measurable and severe and lasted about 2 years. The impact winter was not that. The impact winter was that event, continued. Imagine the year without a summer followed by another year without a summer, and then another and another, and then another year where the summer was weak but noticeable, and then another year of no summer, and keep going. For about a decade, possibly 15 years, The same kind of cooling that Tambora produced for 2 years was produced by the impact, except larger in magnitude and sustained in time. The aerosol load in the stratosphere did not decline on the weekly to monthly timescale of a volcanic eruption. It declined on a multi-year timescale because the particles were finer and they settled more slowly, and a fresh supply from the impact site continued to seed the stratosphere for some time as the vaporized volatiles condensed. The year without a summer, which in 1816 was a disaster that shook European agriculture and caused famines that reset demographic curves in several countries, was, for the earliest Paleocene, just the name for the decade. The biological consequence of that stretched interval is different in kind, not just in degree, from the consequence of a single cold year. A single cold summer causes a crop failure. Plants die, insects die, the animals that eat them go hungry. The next year, if conditions return, the ecosystem recovers. Seed banks in the soil germinate, insect eggs hatch, migratory animals return. The system has capacity for 1 bad year. Some ecosystems have capacity for 2 or 3, but across the time span of an impact winter, every one of the recovery mechanisms runs out of material. The seed bank germinates in the first or second year, the seedlings fail, and that year's seed production, which would normally replenish the bank, does not happen. Insect populations crash, recover a little on what little vegetation remains, and crash again in the next cold year, and the recoveries get smaller each cycle because there is less of everything to work with. Large animals that require a continuous food supply run out of food, run out of body fat, run out of stored metabolic reserves, and die. The entire energetic pyramid that the Cretaceous biosphere had built across its last 30 million years had been tuned for a climate in which bad years were, at worst, 3 in a row. It had no answer for 10 or 15. The work of reconstructing the exact temperature profile of those years has been going on for decades, and the picture has changed as the modelling has improved. The older estimates, based on scenarios in which sulfate aerosols were doing most of the radiative work, tended to produce quite severe cooling. Tropical oceans dropping 6 or 7 degrees, mid-latitude continents freezing catastrophically in summer, high-latitude regions producing temperature anomalies so large that the numbers stop communicating anything useful. More recent modelling, giving fine silicate dust a larger role and revising the sulfur load downward on the basis of new empirical measurements, has produced a somewhat softer picture at the tropical extreme, but a longer duration of the cold overall. This is the pattern of scientific revision, and it is worth being frank about. The numerical details of the impact winter are still in motion. What is not in motion, and has not been since the picture first came together in the 1980s, is the qualitative shape, a sudden severe cooling, a prolonged dimming, and a recovery measured in years rather than seasons. The animals living through it did not experience any of this as a numerical change. They experienced it as the accumulation of small wrongs, none of which any individual generation was equipped to recognize. A hadrosaur hatched in the first year after the impact might have lived, for a while, on the last of the vegetation. The plants still standing, not yet dead, producing some new growth in the weaker sunlight. That animal would have been underweight by the standards of its species, and it would have taken longer to reach maturity if it reached maturity at all. Its mother, which had lived through the first year as an adult, would have been drawing down body reserves from the Cretaceous abundance she had grown up in. By the time the hatchling was an adolescent, its mother was almost certainly dead, and the vegetation it had been eating was almost certainly gone. If that animal bred at all, it bred into a population already thinning. A generation later, there was no population. This is what extinction looks like at the level of individual biology. Not a dramatic collapse, not a single day on which everyone dies, but a protracted pressure applied across lifetimes in which every birth is into conditions worse than the birth before. and every season is shorter than the one that preceded it, and the energy budget of the species as a whole slides toward a negative number that cannot be recovered. Some species were killed in the first hours by fire and shockwave. Most species, including all the large terrestrial ones, died like this, by attrition across years, in a world that kept refusing to come back. The duck-billed dinosaurs that had been so numerous along the Yucatán coast were all gone by the end of the second year, probably, along with their northern cousins. The horned ceratopsians in what is now Montana lasted possibly a little longer because the northern continental interior had a deeper vegetation base to draw down, but they were gone too within a few years. The last tyrannosaurs, which required enormous quantities of meat and which competed for the last healthy prey animals, collapsed as their food base collapsed. Predator populations cannot sustain themselves when the prey density drops below a threshold, because the energetic cost of hunting exceeds the caloric return. In the seas, mosasaurs and plesiosaurs and the long-necked elasmosaurs, top predators that had filled the Mesozoic marine ecosystem for the better part of 100 million years, starved as their food webs unraveled beneath them. Ammonites, which had survived every previous mass extinction in Earth's history, including events in which other large marine groups had been devastated, did not survive this one, and the reason appears to be specific to their biology. Their larvae required a certain abundance of surface ocean plankton to feed on during their earliest developmental stage, and the impact-induced collapse of surface productivity cut off that food supply for long enough that every ammonite egg laid in the first several years produced no viable larvae. When the plankton finally came back, there were no adult ammonites left to lay eggs. A 300 million year lineage ended not because the adults died all at once, but because no new adults could be made. Meanwhile, in 100,000 small places around the planet, animals that had not died in the fire or the dark or the cold, animals that were small, that burrowed, that bred fast, that ate almost anything, continued to live. Their numbers were reduced, their habitats were damaged, their lives were harder than their ancestors had been. But they were there, they were persisting, and while the last of the large animals were dying above them, they were beginning, very slowly, to do what small animals always do in a collapsing ecosystem, which is to spread into the niches that are opening up. The impact winter was hollowing out the biosphere from the top down. What filled in from the bottom would come later, but the cold was not the only thing working on them. The rain during those years was not ordinary rain. In a cliff in the southern Netherlands, near a village called Gulhemmerberg, there is a layer of dark clay sandwiched between two pale yellowish carbonates. The site is quiet, it does not advertise itself, but for a particular question in the chemistry of the impact's aftermath, it is one of the most valuable outcrops in the world. The clay at Gulhemmerberg was deposited in a shallow sea, far enough from the impact site to have received only the fine airborne fallout rather than any coarse ejecta, and it was deposited quickly enough that the interval captured within it is not averaged out by millennia of later mixing. Within that clay, the shells of microscopic surface-dwelling foraminifera, plankton with single-celled bodies and calcium carbonate shells the size of grains of dust, preserve the chemistry of the seawater they had been growing in at the moment of their death. The chemistry of interest is boron. Boron is a trace element in seawater. It exists in two chemical forms, boric acid and borate, and the relative proportions of the two forms depend on the pH of the water they are in. A more acidic ocean contains a different mix of the two forms than a more alkaline one, and the shell-forming organism, in pulling boron out of seawater and incorporating it into its shell, records that mix in a way that can be read back out of the fossil. The technique was developed over decades, refined through cross-checks against modern seawater, and is now reliable enough that a team of geochemists with access to the right mass spectrometers can reconstruct ocean pH across geological intervals with a precision that would have seemed absurd a generation ago. In 2019, a group led by Michael Hennehan, then at Yale, later at a research center in Potsdam, applied this technique systematically across the boundary at Gölheimerberg and at several other sites, and what they found changed the picture of what the impact did to the oceans in a specific and satisfying way. There had been, before this work, a long-running puzzle. The marine fossil record across the boundary is devastated in certain predictable ways. The calcareous plankton crash, the ammonites vanish, the rudest reefs are gone, but the chemistry the survivors recorded in the years and centuries after the impact was strange. The carbon isotopes of shells laid down after the boundary showed a pattern that did not match any simple interpretation. Shells from the surface of the ocean and shells from the deep had almost identical carbon chemistry, which should not have been possible under normal ocean function. Normally, the surface ocean is chemically distinct from the deep because living plankton pull one particular isotope of carbon out of the surface water preferentially, and their bodies, sinking, carry that isotope down. The absence of the normal surface-to-deep distinction in the first Paleocene could mean that the plankton had stopped doing their job entirely, a scenario sometimes called the Strangelove Ocean, named after the Kubrick film, meaning an ocean in which life had, for practical purposes, stopped. But the Strangelove interpretation had a problem. Benthic foraminifera, living on the deep sea floor and depending on organic matter sinking from above, had survived the boundary in very large numbers. If the surface ocean had been dead, the deep ocean should have starved, and it did not. The alternative, known as the living ocean hypothesis, proposed that the plankton had kept reproducing, just not very efficiently. A weaker biological pump, reduced productivity, but not total collapse. The living ocean picture explained the survival of the deep-sea benthics, but did not fully account for the carbon chemistry of the surface. Hennehan's boron measurements resolved it. Both hypotheses had been partly right, and they were not simultaneous. They were sequential. In the first hundreds to thousands of years after the impact, the surface ocean had been acidified so sharply that calcifying plankton could not build their shells fast enough to maintain their populations. Productivity crashed, and the biological pump essentially stopped. That was the Strangelove phase. Then, as the ocean neutralized itself over the following tens of thousands of years through weathering inputs from the land, the pH came back up and the plankton populations began to rebuild, but inefficiently. The ecosystem had been structurally damaged. Many dominant species were gone, and the replacements did not pump carbon to depth as effectively as their predecessors had. That was the living ocean phase. Both real, one after the other. The cause of the initial acidification is what the impact had delivered into the sky, and what had been raining down for the previous several years. The sulfur vaporized from the anhydrite at the impact site did not remain in the atmosphere as sulfur dioxide indefinitely. Over weeks to months it oxidized, combined with atmospheric water, and formed sulfuric acid. Some of it condensed into sulfate aerosol particles that stayed in the stratosphere and contributed to the cooling. Some of it, eventually, inevitably, precipitated. Meanwhile, the impact itself had shocked the atmosphere hard enough to fuse nitrogen and oxygen into nitrogen oxides, which, in the presence of water, become nitric acid. And the vaporized carbonate from the impact site, added to the atmosphere as carbon dioxide, was being partially absorbed by the surface ocean, which converts it into carbonic acid in the surface waters. Three separate acidification pathways, operating in parallel on timescales from days to centuries, all pointing in the same chemical direction. What the surface ocean experienced as a result was a pH drop of something like 1/4 of a pH unit in a geologically instantaneous interval, possibly hundreds of years, possibly less. For reference, the anthropogenic acidification of the modern ocean, driven by the carbon dioxide that industrial civilization has added to the atmosphere since the beginning of the Industrial Revolution, has caused a pH drop of about 1/10 of a unit over 2 centuries, and that has already produced measurable impacts on coral reefs, shelled plankton, and commercial shell fisheries. The impact acidification was roughly 2 to 3 times larger, and happened roughly 10 to 100 times faster. It is the closest natural analogue to what industrial civilization is currently doing, and the comparison is not reassuring in either direction. For organisms that built shells out of calcium carbonate, acidification was not an abstract chemical stress. It was a direct challenge to their structural integrity. At lower pH, calcium carbonate becomes thermodynamically unstable in seawater. It begins to dissolve. An organism that had spent its life building up a shell, pulling calcium and carbonate ions out of seawater and precipitating them into aragonite or calcite, suddenly found itself in water that was dissolving its shell faster than it could repair it. For some species, this simply slowed their growth. For others, it made reproduction impossible. For the most vulnerable, the thinly shelled, the rapidly growing, the larvae that needed to build new shells quickly, it was lethal within a generation or two. The ammonites, already unable to produce viable larvae because of the surface productivity collapse, now could not have built their shells even if their larvae had found food. The rudest bivalves, enormous, reef-building, conical clams that had covered tropical, shallow seas for the last several tens of millions of years, went extinct as a group. The nautiloids, close relatives of the ammonites, but with a slightly different shell structure and broader ecological tolerance, lost most of their species but kept a few. The calcareous nanoplankton, the coccolithophorids whose shells build the chalks of Dover and Kansas, crashed by perhaps 95% of their pre-impact diversity, a collapse so severe that the species that survived are recognizable in subsequent cores as a handful of disaster forms dominating an otherwise empty seascape for hundreds of thousands of years. The planktonic foraminifera, the organisms whose shells Hennehan measured at Gullhemmerberg, lost more than 90% of their diversity as well, reduced in many cases to a single surviving species whose descendants would, over the next few million years, slowly repopulate the diversity tree. The survivors in the sea were predictable once you knew the pattern. Organisms that did not depend on calcium carbonate structures. Organisms whose life cycles were short enough to turn over many generations in the bad interval, selecting rapidly for tolerance. Organisms living in ecosystems whose food webs did not route through surface photosynthesis. Chemosynthetic communities around hydrothermal vents, detritus-based communities in the deep abyss, predators at higher trophic levels that fed on other survivors. A shrimp in a thermal vent community, 50,000 kilometers from the impact, experienced the end of the Cretaceous as a minor change in the chemistry of water filtering down from the surface. A plankton specialist in the euphotic zone of the Tethys experienced it as annihilation. The Gullhemmerberg clay, when you hold it, is not especially impressive to look at. It is dark and soft, and slightly greasy to the touch, and it sits as a thin band between two carbonates that look much more substantial. But inside the clay are the shells of the last foraminifera to have lived in the Cretaceous ocean, and the first to have lived in the Paleocene ocean, and between them, in the pH signal their boron encodes, is the record of how fast the water they swam in became a different substance than what their lineages had evolved to live in. The chemistry in the clay is the reason the ammonites are gone, the rudists are gone, the nanoplankton are reduced to 3 species for the next 300,000 years, and the surface ocean's productivity took tens of thousands of years to recover even the basic shape of its pre-impact function. What recovery looked like and what it left behind is its own chapter. And so is what was simultaneously happening in the water column itself, where the loss of the plankton meant the loss of everything that sank from them. The ocean is, among other things, an enormous machine for moving carbon downward. In ordinary times, in a living, functioning ocean of the kind that existed before the impact and has existed again for most of the time since, the sunlit surface layer of the sea is full of microscopic photosynthetic organisms. These organisms pull dissolved carbon dioxide out of the surface water and convert it into organic matter. They reproduce, they are eaten by other small organisms, their bodies and waste products aggregate into fine particles, and those particles sink. Not all of them make it to the deep sea. Most are consumed or dissolved before they arrive. But enough of them reach the depths that, across the entire world ocean, something like 10 billion tons of carbon per year gets delivered from the surface to the deep. That carbon, once it reaches the deep ocean, is effectively removed from the atmosphere for centuries to millennia, cycling through slow currents that will not return it to the surface until the ocean, at its own pace, turns over. This system has a name. It is called the biological pump, and it is the reason the atmosphere has the carbon dioxide concentration it does rather than a different one. Without the pump, the surface of the ocean would slowly equilibrate with the atmosphere at a substantially higher carbon dioxide level, and the climate would warm. With it, the planet stays in the narrow band of habitability that life has, for most of its history, enjoyed. The biological pump is one of the Earth's most important environmental regulation mechanisms, and it runs, invisibly, on the quiet daily work of organisms too small to see. It stopped. Not entirely, and not everywhere at once, but across most of the sunlit ocean for an interval on the order of tens of thousands of years, the pump essentially ceased to function. The photosynthetic organisms that ran it had been killed by the combination of darkness, cold, and acidification already described. The organisms that ate them had nothing to eat. The aggregation of sinking particles that had been the pump's output slowed to a trickle. The surface ocean stopped receiving fresh carbon delivery from photosynthesis, and the deep ocean stopped receiving the rain of organic material that its ecosystems had, for hundreds of millions of years, been built around. If you had been able to sample seawater from that interval, at the surface, at the middle depths, at the deep sea floor, and measure its carbon isotope chemistry, you would have found something that should not have existed in a normally functioning ocean. The surface water and the deep water had the same signature. Their isotopic fingerprints were indistinguishable. In an ordinary ocean, the surface is enriched in the heavier carbon isotope because the photosynthetic organisms preferentially pull the lighter one into their bodies, and those bodies, sinking, carry the lighter isotope down, leaving the surface relatively heavy and the deep relatively light. The gradient between them is measurable, predictable, and a direct signature of a working biological pump. In the boundary interval, that gradient is gone. The two layers are chemically identical because nothing is moving between them. This is the Strangelove state, the ocean at its quietest. It is not strictly a dead ocean. Life persists in it. The benthic foraminifera on the deep sea floor survive the interval in large numbers, quietly, drawing on existing stores of organic matter and on whatever trickle of new material still manages to arrive. Chemosynthetic communities at hydrothermal vents, which depend on geothermal energy rather than surface sunlight, carry on without noticing. Predators capable of feeding on the survivors of the acidification crisis, small fish, cephalopods, a handful of surviving planktonic lineages, hold on. What the Strangelove state marks is not the death of the ocean, but the silencing of its primary metabolic machinery. The surface is no longer producing. The deep, is no longer receiving. The pump has stopped, and for as long as it is stopped, the ocean as a whole is running on stored capital. The persistence of benthic foraminifera through this interval is one of the crucial data points for understanding what actually happened, and it is the reason the original Strangelove formulation proposed in the early 1980s could not be the full story. If the surface ocean had been completely dead, no photosynthesis, no organic rain, then the benthic community on the deep sea floor should have starved within a few decades because the carbon reserves available to them in the deep sediment are finite, and renewal depends on ongoing surface productivity. The benthic foraminifera did not starve. They persisted in altered communities, but with many of the same species straight through the boundary. Which means the surface ocean, even at its quietest, was not entirely dead. Something was still sinking in reduced quantities, enough to keep the deep ecosystems alive. The system was not a switch from on to off. It was a switch from working to barely working, and the barely is what carried the deep sea community across the interval. That barely matters for everything that comes next in the ocean's story. Around 10 to 100,000 years after the impact, in a timescale governed by chemical weathering of exposed rock on the continents, the surface ocean began to chemically recover. Rivers, loaded with weathered calcium and carbonate ions from land where the boundary clay had protected nothing, delivered alkalinity to the sea. The pH climbed back out of its crisis value. Calcium carbonate became thermodynamically stable at the surface again, and the surviving photosynthetic organisms, reduced to a few disaster forms, began to multiply. They did not rebuild the pre-impact ocean. They rebuilt a different ocean, one dominated for hundreds of thousands of years by a handful of species, each of them numerically abundant but taxonomically impoverished. The calcareous nanoplankton crashed from perhaps 100 species to fewer than 10, and the 10 that persisted were specific survival forms, small and adaptable, that bloomed in successive pulses as conditions fluctuated. The planktonic foraminifera were, for a while, reduced to essentially one species, a single surviving lineage from which all subsequent planktonic foraminifera descended. A whole evolutionary tree of microscopic ocean life collapsed to a single stem from which every modern planktonic foraminifer alive today is descended. This is the living ocean phase, productivity returning, but inefficiently and in a shape that did not match what had come before. The biological pump worked again, but weakly. The carbon isotope gradient between surface and deep began to reappear, but muted. The shell rain resumed, but thinned. In the sedimentary record, this shows up as an interval of very slow carbonate accumulation, what paleoceanographers call a boundary clay, or, in deeper sites, a break in the otherwise continuous rain of calcareous sediment. Looking at a deep sea core from the appropriate age, you can see the line. Thick, white carbonate below, a thin, dark band that is the boundary, and above it a slow return to lighter, carbonate-rich sediment over hundreds of thousands of years. The ocean's colour written into its own floor. The full recovery, by which is meant the return to diversity and ecological complexity comparable to what had existed in the late Cretaceous, took much longer. Morphological disparity in the planktonic foraminifera, the range of shapes and sizes and functional strategies those organisms explored, did not return to pre-impact levels for something like 5 to 10 million years. The calcareous nanoplankton rebuilt their taxonomic diversity on a similar timescale. The coral reefs of the pre-impact world, devastated by the loss of the rudest bivalves that had been their primary architects, did not return to their previous structural complexity for tens of millions of years, and when they did, it was with a different cast. The modern scleractinian corals, which had been minor ecological players in the Cretaceous, inheriting a world in which their previous competitors were simply gone. What is remarkable, from the point of view of how long this took, is how unremarkable it is from the point of view of geological time. 5 million years is not, by the standards of the Earth's biography, an eternity. It is less than the time it took for the first human ancestors to walk out of Africa and establish themselves on every continent. It is less than the age of the grass family, which in turn is less than the age of the flowering plants, which in turn is less than the age of the dinosaurs the impact had just killed. For the planet, the Strangelove and living ocean recovery was a relatively brief adjustment. For the species living through it, it was the only world there was, and the world was thin. This is where the scale discipline starts to strain, because the listener is being asked to hold two different temporal registers at once: the planetary clock, on which 5 million years is a short recovery, and the biological clock, on which 5 million years is so long that no single species, no single lineage, no single ecosystem encountered the pre-impact and post-impact worlds as the same thing. You are, at this point, halfway between them. Your own mammalian lineage survived the interval as something small and unspecialized, radiated into the empty niches the impact had opened up, and over those same 5 to 10 million years began to acquire the basic body plans that would eventually lead to you. The ocean was rebuilding itself on the same timescale that your ancestors were diversifying. What the ocean's rebuilding left unfinished on land was a great deal. The terrestrial record of that same interval is, in its own way, as catastrophic as anything happening in the water, and some of its most important losses happened not to the large animals whose disappearance the extinction is usually named for, but to the organisms that had made the forests themselves. In a canopy of a Cretaceous conifer forest in what is now Patagonia, a small feathered creature, roughly the size of a starling, was incubating a clutch of eggs. The creature was not a bird in the modern sense, though it had feathers and wings and a beak, and if you had glimpsed it moving through the branches, you would have had no difficulty calling it a bird. It belonged to a lineage paleontologists sometimes call the enantiornithines, the opposite birds, named for an anatomical quirk in the way their shoulder bones articulated. And they had been, for most of the Cretaceous, the dominant small flying animals on land. They filled the niches that today are occupied by songbirds, kingfishers, small parrots, and woodpeckers. They had diversified across every continent. They nested in tree hollows and built nests in branches. They ate insects and seeds and small fruits and sometimes each other. By the end of the Cretaceous, there were more species of enantiornithines in the world than there are species of any single modern bird family, and their fossils have been found from the Arctic to Antarctica. Not a single enantiornithine survived the impact. Across the boundary, in sediments deposited in the centuries after, their fossils simply stop. The small creature in the Patagonian canopy, on its eggs, is an example of 1,000 such individuals across the world that morning. Abundant, successful, ecologically central, and within the next several years, completely gone. Their lineage, hundreds of species, 100 million years of evolutionary history, ended in the impact's aftermath so thoroughly that the group is now known only from bones. What survived among the birds was a small and quieter group of ground foragers and shoreline waders, and a handful of lineages living near freshwater, the ancestors of modern birds, the neornithines, which at the time of the impact were themselves a minor evolutionary experiment. They did not survive because they were better adapted in any general sense. They survived because, when the forests collapsed, they were not in the forests. The forests had been the problem. In the hours and days and years after the impact, the most severely damaged terrestrial ecosystem was the one that had been most vertically structured, the closed canopy forest. These forests, covering substantial fractions of the continents through the late Cretaceous, had been dense, multi-layered, and dependent on continuous sunlight reaching the canopy and filtering down to the understory. The thermal pulse had burned large portions of them in the first hours. The ensuing darkness had killed the surviving canopy trees by starving them of the light their biomass required. And the loss of the trees, across millions of square kilometers, erased the three-dimensional habitat that had been the home of a very particular ecological type, the arboreal specialist, the animal whose body plan, diet and behavior had all evolved to exploit a life spent above the ground. The enantiornithines were one such type. The arboreal Mesozoic mammals, a diverse group that included both early Therians and more archaic lineages, were another. Arboreal lizards, arboreal frogs, arboreal invertebrates, the specialized insect communities that lived in canopy microhabitats, all of them, in the years after the impact, lost their world. The selectivity pattern that emerges from the terrestrial fossil record, once the dust settles on the first 100,000 years, is clean enough that it looks almost designed. Large animals died. That is the pattern that has been noticed longest and the one that popular accounts usually emphasize. No non-avian dinosaur survived. No pterosaur survived. The large marine reptiles, mosasaurs, plesiosaurs, died. The rough cutoff for terrestrial tetrapods was body mass. Almost no land vertebrate weighing more than about 25 kilograms made it across the boundary. A few exceptions in ectothermic lineages, crocodilians, turtles, some large snakes, crossed the line, but those exceptions are ecologically explicable. An ectothermic animal can survive a long interval without food because its metabolic rate is low enough that body reserves last. A large endothermic animal cannot. The 25-kilogram cutoff is, in effect, a metabolic cutoff. Above it, in an endotherm, the energy requirement per day is large enough that a prolonged food crisis is fatal. Below it, an animal can shelter, slow down, wait. Small animals, by the same logic, did better. Most small terrestrial vertebrate lineages made it through in some form, though usually with heavy reductions. But body size alone does not explain the pattern, because plenty of small arboreal animals died too. Size was the first filter. Habitat was the second. The ground dwellers survived disproportionately. The tree dwellers were eliminated. Diet was the third filter, and perhaps the most interesting. Animals that depended directly on living plants, herbivores eating fresh vegetation, pollinators visiting flowers, specialist seed predators feeding on particular plant species, struggled most. Animals whose food chains did not route through living photosynthesis did better. This is why freshwater ecosystems survived the boundary far better than terrestrial ones. The base of a freshwater food web is often not fresh plant biomass, but detritus, decaying leaves, sunken wood, organic particles drifting down from the bank. A river in the boundary interval, whose surrounding forest was dying, actually received an increase in detrital input for a while as the forest shed its leaves and dropped its branches and eventually toppled. The detritivore-based food webs of rivers and lakes, crayfish, freshwater mollusks, bottom-feeding fish, the amphibians and turtles and crocodilians that ate them, had a food source that the terrestrial ecosystems above them had lost. They took reduced losses across the boundary, which is why freshwater ecosystems today are still disproportionately staffed by lineages that are very old. So the filter, looked at honestly, was this: be small, be near the ground, and don't depend on living plants for your calories. Anything that fit that description had a fair chance. Anything outside it did not. The dinosaurs were outside it comprehensively, large, mostly terrestrial or aerial rather than aquatic, and at the top or near the top of living plant-dependent food chains. Their extinction was not, as is sometimes implied, arbitrary or bad luck. It was the predictable consequence of the filter applied to the ecological position they happened to occupy. There is a question worth pausing on here, because it is the kind of question the material invites, and the channel does not usually dodge. Is extinction the right word for what happened to the dinosaurs? On one reading, it clearly is. No non-avian dinosaur lineage made it across the boundary. Every species, every family, every body plan that had been identifiably dinosaurian is gone. In that sense, the word is exactly accurate. The group was extinguished. On another reading, it is the wrong word, because the only reason there is a word for it at all is that the descendants of the dinosaurs that did survive, the Neornithine birds, were successful enough to populate the modern world with somewhere around 10,000 species, and for most of human history, those descendants were not classified with their ancestors. We separated the birds from the dinosaurs taxonomically, treated them as different kinds of thing, and then noticed much later that the separation was artificial, that birds are, in the strict cladistic sense, dinosaurs. They are theropod dinosaurs of the Coelurosaurian subgroup, descended from small feathered ancestors of the kind that, in the Cretaceous, ran around beneath the feet of tyrannosaurs, which means the dinosaurs as a clade are not extinct. They are, in terms of species diversity, more successful now than they have been in all but a handful of intervals of their history, because 10,000 species of living bird is a lot of species. The dinosaurs did not end. Most of the dinosaurs ended. Some of the small, feathered, endothermic, rapidly reproducing ones did not end, and everything now airborne and singing is what those survivors across 66 million years became. So, extinction is partly right and partly wrong at the same time. It is right if you mean the loss of the adult, charismatic, recognizable forms that defined the Mesozoic. It is wrong if you mean the ending of the lineage, and the reason the word feels right to a listener anyway is that the popular image of dinosaur means specifically the adult, charismatic, recognizable forms. What the impact killed was most of the dinosaurs. What it left alone was a handful of their smaller cousins, and from those it made birds. This is a pattern that will repeat in other forms through the rest of the story. The word extinction, applied to a major boundary, always carries a partial truth and a partial misdirection. The mammals you are descended from at the moment of the impact did not feel themselves to be inheriting anything. They felt small, cold, and mostly hungry, and the 66 million years of mammalian expansion that led to you was invisible to them in exactly the way the 10,000 species of modern birds would have been invisible to an enantiornithine on her eggs in that Patagonian canopy. What we now read as a clean selective filter was, to anyone living through it, a generations-long ordeal of bad seasons and thinning forests and mates not coming back in spring. The creature on her eggs that morning, 66 million years ago, was incubating a lineage that had no future. But within a few kilometers of her nest, in the leaf litter below the trees, something else was moving. Something small, warm-blooded, uncharismatic, and generally ignored by the larger animals in the canopy. And that something was incubating, in its own way, a lineage that did. Underneath a root system in what is now Colorado, during a winter that came in the third year after the impact, a small animal was alive in a chamber it had dug the previous autumn. The chamber was roughly the size of a grapefruit. The animal was smaller, palm-sized, with dense fur, a long, thin tail, and a sharp, conical face built around an insectivore's teeth. By the standards of any Mesozoic observer, had one existed, it would have been unremarkable. One of the small, warm-blooded nocturnal creatures that had scurried through the underbrush beneath the feet of the dinosaurs for over 100 million years, and that no large Cretaceous predator would have bothered to remember between meals. The lineage it belonged to had existed in roughly that body plan since the Jurassic. It had, across all of that time, never been ecologically central to anything, had never produced a large-bodied species, had never dominated a habitat, had never done anything that a textbook would find worth recording. It was, by every measure of Mesozoic success, a minor lineage. It was your ancestor. Not directly. There are 66 million years of generations between that animal and any person listening to this. But the lineage that would eventually produce primates, and from primates the great apes, and from the great apes the human species, ran through animals that looked and lived very much like this one in the winter after the impact. Small, warm-blooded, burrowing, omnivorous, not in any of the places where large and visible animals were dying, not, in fact, in any place a Cretaceous visitor would have thought to look. If you had crouched above the leaf litter at the entrance to that chamber, on that particular night in that particular winter, and if you had been able to see in the dark, which the creature below you could, you would have seen something doing what its kind had always done. Not enduring an apocalypse, just sleeping slowly, conserving heat against a cold that was worse than usual, but was, in its essentials, just cold. Breathing slowly, dreaming whatever small dreams small mammals dream. The sky burning that had ended the world of the large animals above had not reached down to this. The darkness that had starved the forests was irrelevant to an animal that came out only at night and ate mostly insects and the occasional egg. The cold was, by then, the hard fact of its existence, but its body plan had strategies for cold that the hadrosaurs had never developed. Dense fur, the ability to shiver, the ability to reduce its own metabolism in torpor, the social heat of huddling with others of its kind. The impact winter was a bad season in a string of bad seasons, and the animal had been, for all of its short life so far, getting through bad seasons. The popular version of this story says, the mammals inherited the Earth because they were better, smarter, warmer, cleverer, more adaptable, all the qualities the popular version of evolution loves to project backward onto winners. The popular version is wrong. The mammals did not inherit the Earth because they were better. They inherited it because they had, by complete accident, been a lineage whose existing body plan happened to fit the set of traits that the impact's filter selected for, and they had been waiting underneath the dominant ecology for so long, underneath the dinosaurs, underneath the crocodilian relatives, underneath the large synapsids that had preceded them, that their waiting was not a strategy so much as a habit. They had developed the small, warm, nocturnal burrowing form 150 million years earlier during the Jurassic, in conditions that had nothing to do with asteroid impacts, and they had kept it through every subsequent shift in the Mesozoic world. They were not hiding. They were living in the ecological positions they had evolved into, as every organism does. Those positions happened on the particular morning 66 million years ago when the sky caught fire, to be the positions that turned out to be survivable. There is a certain kind of humility in this observation that I want to be careful not to overstate. The mammals did not succeed because they were weak or small or modest. They succeeded because they were alive after the filter. Every lineage alive after a mass extinction is, by definition, a lineage that was positioned correctly for that particular filter. In the end Permian event, 180 million years earlier, it had been a different filter, and different lineages had been positioned correctly. In the end Ordovician, earlier still, it had been different again. The notion that you can predict survival from general virtues, that cleverness or adaptability or some other positive trait is a reliable predictor across extinction events, does not hold up to scrutiny. Cleverness and adaptability are usually specific to particular environments, and a clever organism adapted to a Cretaceous forest ecosystem was exactly as dead as a stupid one after the forest was gone. What the survivors all shared across every mass extinction in the record is not a positive trait, but a kind of double luck. First, they happened to have a body plan or ecology that matched the specific filter of the specific event. Second, they happened to be alive in the place and time that the filter operated. Neither of these is a virtue. Neither reflects well or badly on the lineage. They are, collectively, the conditions under which anything at all survives, when most things do not. And this is the point at which the story becomes personal, in a way it has not been so far. You are listening to this because the mammal in the chamber under the root system in Colorado, in a winter in what is now the state of Colorado, but was then an enormous floodplain emerging from a shallow inland sea, lived through that winter. It lived through the next winter and the one after. It mated in some spring when mating again became possible. It raised a small and unremarkable litter of young. One of those young grew up and mated and raised a litter. A lineage thin and tentative in those first generations continued. Then the lineage widened, slowly, as the forests began to return, as the insect populations rebuilt, as the impact winter faded, and the long Paleocene recovery gave small mammals more space than they had had in 150 million years. Across 10,000 such lineages that survived in pockets around the world, in Colorado burrows, in Montana streambeds, in hollows of fallen logs in what is now Europe, in the high Andean sides of Cretaceous mountains, the mammals expanded into the niches the dinosaurs had left empty. The expansion took time. The first Paleocene mammals were not the modern, varied, large-bodied groups you would recognize. They were, for the first 5 or 10 million years, still small, still unremarkable, still doing the same things their Cretaceous ancestors had done, just with slightly more room. But the room was the key. The filter had removed the ceiling that had, for the entire Mesozoic, kept mammals small. Once that ceiling lifted, the mammals diversified at a rate that, by the standards of ordinary evolutionary time, was very fast. The first hoofed mammals appear in the fossil record within a few million years of the boundary. The first primate-like forms appear within 10. Whales, cats, elephants, horses, all of them descendants of small Paleocene mammals that were, in the immediate aftermath, difficult to tell apart from one another. The modern mammalian world is a 10 to 60 million year recovery of the one niche space that had been locked off for the better part of 200 million years. And somewhere in that expanding set of lineages, through a series of ecological shifts, out of the burrow and into the trees, into canopies, into sleeping at night and rising during the day, into larger body sizes, into better color vision, into tool use, into cooperative hunting, into speech, an unbroken thread ran forward to a particular evening on which a particular descendant of that small winter animal, 66 million years later, lay in a quiet room listening to a voice describe what its ancestor had done by surviving. The thread was never a guarantee. At any point in those 66 million years, the thread could have broken. A different extinction event, a different ecological accident, a different evolutionary branch, taking a path that did not lead here, and there would be no one listening. There is no law of nature that required this sequence to produce you. There is only the record that it did. This is worth sitting with for a moment, because it is the kind of fact whose weight tends to get lost in either direction, either flattened into "we are miracles," or dismissed as "everyone has ancestors, so what?" Both flattenings miss what is actually remarkable, which is not that you exist, but that the specific conditions under which you exist are traceable. The winter chamber in Colorado. The small insectivore sleeping through a bad year. The unbroken maternal line running forward through every subsequent ecological crisis and recovery, never once failing to produce a next generation across an interval of time longer than the existence of grass. Your own lineage still here, you still listening. a planet that has been destroyed before, and maybe again, but that in the narrow interval between the last ending and whatever the next ending is, produces organisms capable of understanding what happened before they arrived and of thinking about it quietly, in the dark. The small things that waited without any idea that they were waiting for anything. They simply continued. And because they continued, everything that is now alive that descends from them continues too, until such time as it doesn't. The planet's time goes on either way. The impact, the darkness, the cold, the acid, the silent ocean, the dying forests, the 25-kilogram line, all of that had, by a few million years after the event, receded into the background, into a new stability. What remained of interest in the millions of years that followed was not the catastrophe, but the question of why it had happened. And that question did not get asked until the species that was asking it had been generated out of the survivors and had, eventually, learned to read the rocks. That is a much later part of the story. But the reading began, in earnest, with a single observation made at the edge of a quiet Italian town in the 1970s. What Walter Alvarez was trying to measure in the Umbrian limestones in the summer of 1977 was the Earth's magnetic field. Not the modern field, the ancient one. The limestones of the Apennines had been deposited on a deep seafloor, and in the slow precipitation of calcareous mud onto that seafloor, tiny iron-bearing mineral grains had aligned themselves with whatever direction the Earth's magnetic field had been pointing at the time of their formation. Once the mud compacted and hardened, those alignments were locked into the rock. Across tens of millions of years of deposition, the Earth's magnetic field had reversed its polarity dozens of times, and each reversal was preserved in the limestone as a change in the direction of those locked-in grains. Alvarez was a young geologist working for the Lamont Doherty Earth Observatory in New York, and his project was to build a detailed paleomagnetic chronology, a timeline of those reversals, that could be used to calibrate the ages of Mesozoic rocks around the world. The sequence at Gubbio was ideal for the work. The exposure at a place called the Bottaccione Gorge, a short walk from the medieval hilltop town, showed hundreds of meters of pelagic limestone in continuous deposition, covering the transition from the Cretaceous to the Paleogene. Every meter of limestone represented thousands of years. Every centimeter could be sampled and measured. The work was meticulous and slow, and Alvarez was good at it. Running through the sequence, at a consistent horizon, there was a thin layer of dark clay. The clay had been known for more than a century. Italian geologists had mapped it, described it, and moved on. It was approximately 1 centimeter thick, soft, slightly greasy, and recognizable by eye. It sat between the pale, creamy limestones of the late Cretaceous and the pale, creamy limestones of the early Paleogene, and its position coincided with a sharp change in the microfossils of the surrounding rock, a widespread disappearance of many species of planktonic foraminifera at the top of the Cretaceous, followed by their gradual rebuilding in the Paleogene. The disappearance was called, in the older literature, the Cretaceous Tertiary or KT boundary, and it was known to correspond globally to a major biological event. Exactly what the event was remained open. Several hypotheses were in circulation: gradual climate change, global volcanism, a supernova exploding nearby, a shift in ocean chemistry, and none of them had strong supporting evidence. What Alvarez wanted to know was how long the clay had taken to form. The question was not really a question about extinctions. It was a question about sedimentation. If the clay represented a long interval of slow deposition, tens of thousands of years, say, during which the usual rain of calcareous shells had stopped because the organisms producing them had died, that implied one kind of story. If it represented a brief event, a few hundred years or less, that implied a different kind of story. The The micropaleontology could not distinguish these. The rock itself did not contain enough datable material to constrain the interval directly. But Alvarez thought there might be a different clock available. He mentioned the problem on a visit home to his father. Luis Alvarez was by then one of the most distinguished physicists alive. He had won the Nobel Prize in 1968 for his work on subatomic particle detection. He had built the first hydrogen bubble chamber at the scale needed to find new particles and discovered several in the process. He had worked on the Manhattan Project. He had flown in an observation plane alongside the Enola Gay over Hiroshima. In later life, he had turned for amusement to problems outside his formal field. He had used cosmic ray muons to search for hidden chambers inside the Egyptian pyramids and had analyzed the Zapruder film of the Kennedy assassination for ballistics. He was, among other things, the kind of scientist who took a sun's rock sample seriously and immediately began thinking about what instrument could be brought to bear on it. His suggestion was iridium. Iridium is a platinum group metal, and on Earth's crust it is vanishingly rare. It is denser than almost anything, and in the molten early Earth nearly all of it sank into the core, along with the other heavy siderophile elements. What remains on the surface, in ordinary terrestrial rock, is present at parts per billion concentrations at best, and often parts per trillion. But iridium is not rare in the solar system as a whole. Meteorites contain it at much higher concentrations than Earth's crust does, which means that some small, steady amount of iridium is delivered to Earth's surface continuously as extraterrestrial dust and micrometeorites raining down through the atmosphere and settling into sediments at a slow but approximately constant rate. If Luis was right, the clay layer at Gubbio could be dated by its iridium content. The logic was straightforward. If the clay had formed slowly, over tens of thousands of years, it would contain a substantial accumulation of the steady extraterrestrial iridium influx, maybe 10 or 20 times the background found in the surrounding carbonates. If the clay had formed quickly, during an interval in which the calcareous plankton had stopped sinking, but ordinary sedimentation had otherwise continued, the iridium content would be only a little higher than the background. Measure the iridium. Read off the duration, a chemical clock for a geological moment. To measure parts per trillion concentrations of a trace metal in a rock, you need specialized instruments and specialized people. The Alvarezes took their samples to two chemists at the Lawrence Berkeley Laboratory, Frank Asaro and Helen Michael, who had developed a technique called neutron activation analysis. The method worked by placing the sample in a nuclear reactor, where certain elements within it absorbed neutrons and became temporarily radioactive. Each radioactive isotope decayed with its own characteristic energy signature, which could be read by a gamma-ray spectrometer. By counting the signatures and calibrating against known standards, Asaro and Michel could measure dozens of elements simultaneously, at concentrations that ordinary chemistry could not touch. They had, at the time, the best low-level iridium measurement capability in the world. They ran the Gubbio samples in 1978. The result was not what anyone had expected. The iridium concentration in the clay was not 10 times higher than in the surrounding carbonates. It was 600 times higher. The number did not fit. At the delivery rate expected for ordinary extraterrestrial dust, a 600-fold enhancement would imply a clay-forming interval of millions of years, during which essentially no terrestrial sediment had been deposited. That was impossible. The stratigraphy around the clay ruled it out. Either the iridium had not been delivered by ordinary extraterrestrial dust, or some other source had contributed. Asaro and Michel tested for alternatives. Could the iridium be local? No. The underlying and overlying carbonates had ordinary concentrations. Could it be a laboratory contamination? No. They reran the measurements. Could it be supernova fallout from a nearby stellar explosion? This was a serious possibility, and one the Alvarezes considered carefully. A supernova close enough to Earth would have delivered a pulse of heavy elements into the atmosphere, and some of them would have ended up in the clay. But a supernova would also have delivered plutonium-244, an isotope not produced by ordinary stellar nucleosynthesis, but generated in supernova explosions. Asaro and Michel checked for plutonium-244. There was none. That left one explanation the data seemed compatible with. The iridium had been delivered as a single pulse, rapidly, in quantities far exceeding ordinary cosmic dust. The kind of delivery that would occur if a large extraterrestrial object, rich in iridium, had struck the Earth at the boundary and vaporized itself into the global atmosphere, from which it had settled into the sediments being laid down at that moment. The hypothesis was that a very large asteroid or comet had hit the Earth 66 million years ago, and that its vaporized remains had formed the thin clay layer that geologists had been walking past for 100 years. Before the Alvarez paper reached publication, a separate and entirely independent line of work reached a parallel conclusion. Jan Smit, a Dutch paleontologist, had been studying the boundary interval at a site in Caravaca, in southern Spain, and had noticed the same kind of thin clay layer. Smit had sent samples to a different laboratory. The iridium enhancement was the same. The conclusion was the same. Smit's findings were presented and circulated in 1979, slightly before the Alvarez team's paper appeared in print, and the two discoveries have been jointly credited in the broader scientific recognition of the effect, even if the Alvarez paper is what most people remember. The Alvarez paper appeared in Science in June of 1980 under the title Extraterrestrial Cause for the Cretaceous Tertiary Extinction. It was careful. The dinosaurs were mentioned, but the main claim was about the iridium itself and what it implied. An impact of an object roughly 10 kilometers in diameter, producing a crater somewhere between 100 and 200 kilometers across, delivering enough atmospheric disturbance to account for the global biological event at the boundary. The paper was explicit that the exact killing mechanism was uncertain and that further investigation was needed. The reception was not gentle. Paleontologists, many of whom had been working on gradual extinction hypotheses for decades, found the paper's proposal jarring. Several prominent figures in the field dismissed it on stratigraphic grounds, arguing that the extinction was not actually simultaneous and that a single cause could not account for the pattern. Geologists proposed volcanic alternatives, that a period of unusually intense volcanic activity could have produced iridium-rich fallout from deep mantle sources without requiring an impact at all. That alternative would prove unusually persistent. The debate between impact and volcanism would continue at diminishing volume for the next several decades, and in one form or another is still not fully closed. For several years after the 1980 paper, the scientific community was genuinely divided, and the argument became sharp enough that papers were published criticizing the Alvarez hypothesis in strong terms, some by eminent researchers. The term impact hypothesis was, through the early 1980s, a hypothesis and not yet a conclusion. What the hypothesis needed to settle the argument was a crater. A 600-fold iridium enhancement in a thin clay layer is circumstantial evidence of an impact. A structure of the right size, at the right place, with the right age, would be proof. In 1980, as far as the scientific community knew, no such structure existed. Nothing on the continental surfaces of the Earth matched the requirements. The oceans, which cover most of the planet, had not been thoroughly mapped for such a feature, and attention turned first to the seafloor. The search began in earnest, and it turned out to take longer than anyone expected, partly because the evidence for the crater had by then already been sitting in a filing cabinet in Mexico for 2 years under the care of a geophysicist nobody in the impact hypothesis community had ever spoken to. In a filing cabinet in a Pemex office in Mexico City in the autumn of 1978, there was a map that nobody who needed to see it would see for another 12 years. The map had been produced by the Mexican National Oil Company during an airborne magnetic survey of the Gulf of Mexico, a routine piece of prospecting work aimed at finding new offshore petroleum reserves. The survey had flown a grid pattern over the northern coast of the Yucatán Peninsula and the adjacent shelf waters, measuring subtle variations in the Earth's magnetic field caused by differences in the density and composition of the rocks below. Most of what such a survey produces is noise, or else patterns that are interesting only if you are drilling for oil. But in the data covering the Yucatán margin, 2 geophysicists assigned to the project had found something else. Glenn Penfield was one of them. He was an American, working as a contractor on the survey, and he was good at his job. His colleague Antonio Camargo was a Pemex staff geophysicist. Together, when they pulled the filtered magnetic data into a map, they saw a roughly circular anomaly, an arc of strong magnetic signal offshore running in a curve that suggested a full buried ring about 180 kilometers across. The center of the ring sat near a small coastal town called Chicxulub Puerto. The two of them knew what they were looking at, or thought they did. A buried circular structure of that size, in rocks of the right age, had the geophysical signature of an impact crater. Penfield pulled the old gravity maps of the same area from the Pemex archive, maps made decades earlier during a different survey. And the gravity anomaly was there too, centered on exactly the same ring, confirming the signature. He and Camargo wrote up their interpretation and took it to their managers. The response was not enthusiasm. Pemex was not in the business of paleogeology. The company's interest in the anomaly was limited to whether it suggested hydrocarbons, which it did not, or at least not in any form the exploration team cared about. Penfield and Camargo were allowed to present a short paper on the structure at a technical conference of petroleum geophysicists in Los Angeles in 1981, on the condition that they not share the proprietary survey data itself. They presented the paper. The audience was small. The Alvarez hypothesis, published the year before, was already the subject of intense discussion in an entirely different scientific community. Paleontologists, geochemists, planetary scientists, none of whom were attending this particular petroleum industry conference. The two descriptions, of the 10-kilometer impactor hypothesis and of a 180-kilometer buried crater of roughly the right age in roughly the right part of the world, sat in different scientific silos, and the people who should have noticed the overlap did not. Penfield, aware that his structure might be relevant to the larger debate, tried to get the word out. He wrote to Walter Alvarez directly, describing what he and Camargo had found. Walter Alvarez, at that time, was receiving a great deal of mail, much of it from people who were very certain they knew where the impact crater was, most of them wrong. The letter from Penfield did not produce a response, not because it was dismissed or even particularly noticed. There was simply too much incoming correspondence, and a letter from a petroleum geophysicist about a buried structure he had seen in proprietary survey data, with no published peer-reviewed account of the finding, was not obviously the signal in the noise. The letter sat in a pile. The pile got filed, or lost, or thrown away. Walter Alvarez has said in subsequent accounts that he does not remember receiving it. So Penfield's map stayed in its drawer. Camargo returned to other projects. The 1981 conference paper went into the archives of the Society of Exploration Geophysicists, where it was findable in principle but not in practice. And the search for the crater went on through the 1980s in several wrong places. The searching itself is worth briefly describing because it shows how scientific consensus moves even when the answer is already known somewhere else. Through the first half of the 1980s, attention focused on the deep ocean on the assumption that an impactor of the relevant size would have left a crater on the seafloor. Most of the Earth's surface is oceanic, so statistically, that is where one would expect to find it. Survey cruises were organized. Sediment cores were examined for ejecta markers. Candidate sites were proposed and then rejected as their ages or sizes failed to match. One plausible candidate was a structure off the northwest coast of Cuba. Another was a possible feature on the Caribbean seafloor. Neither matched on closer examination. Meanwhile, the chemical and mineralogical evidence at the KT boundary was accumulating rapidly. The iridium anomaly was confirmed at site after site. Stevens Clint in Denmark, Woodside Creek in New Zealand, Caravaca in Spain, El Kef in Tunisia, and the layer's global extent became difficult to dispute. Shocked quartz grains with the specific planar deformation features produced only by impact pressures were identified by Bruce Behor at the US Geological Survey. Tiny glass beads, tektites and microtektites were found at the boundary in several places. In Haiti, on the island of Hispaniola, an unusually thick deposit of such beads was identified at the boundary, and its thickness suggested that it had been deposited close to the source. Researchers began to narrow the search toward the Caribbean and the Gulf of Mexico. The crater was near. They just could not find it. The connection finally happened in 1990 through a journalist. Carlos Baez was a science reporter for the Houston Chronicle. He had been following both the impact hypothesis debate and, separately, the Penfield and Camargo story, because Houston is a petroleum industry town, and the 1981 SEG conference paper had been visible locally in a way it had not been nationally. Baez had known Penfield for years. He had also been following the work of Alan Hildebrand, a graduate student at the University of Arizona who was investigating the Haitian tektite deposits as part of his doctoral research. Hildebrand and his advisor, William Boynton, had been independently converging on the idea that the impact site was somewhere in the Caribbean. Baez, having known both the Penfield story and the Hildebrand research, made the connection nobody else had been positioned to make. He told Hildebrand about Penfield's work. Hildebrand called Penfield. They compared notes. Penfield described the buried ring and the gravity and magnetic signatures. Hildebrand described the Haitian tektites and the accumulating case for a Caribbean site. Each of them recognized almost immediately what the other had. Hildebrand and Boynton then tracked down the original Pemex drill core samples from the Chicxulub structure, which had been archived decades earlier and which, in some cases, had been misplaced or destroyed. They found enough material to examine. The samples contained shocked quartz. The samples contained impact breccia. The samples contained glass with chemistry matching the Haitian tektites. Everything fit. The joint paper by Hildebrand, Penfield, and several other authors appeared in Geology in September of 1991, announcing the identification of the Chicxulub structure as the impact crater responsible for the KT extinction. The paper was careful, rigorous, and extensively footnoted. It cited the 1978 Penfield and Camargo work. It cited the Alvarez hypothesis. It laid out the geophysical, mineralogical, and chemical evidence in parallel. And it closed the question that had been open for 11 years. The crater that had left the iridium in the Gubbio clay was under the Yucatán shelf, buried beneath a kilometer of younger sediment, and it had been there the entire time. What makes the story worth pausing over, and what popular accounts of the Chicxulub discovery tend to skim past, is the 12-year interval between the first identification of the structure and its recognition by the scientific community that needed it. That interval is not a story about intellectual failure. Penfield and Camargo did their work correctly. The Alvarez team did their work correctly. The boundary chemists did their work correctly. Each of them, in isolation, produced sound results. What failed for those 12 years was the mechanism by which those results could find one another. Scientific disciplines in practice are communities of attention. Each discipline reads its own journals, attends its own conferences, follows its own debates. Information that belongs to one discipline does not automatically reach another, even when the information would resolve a question in the other discipline. The petroleum geophysicists who knew about the Yucatán structure were not reading the paleontology literature. The paleontologists looking for the crater were not attending petroleum conferences. The Alvarez team, sitting in physics and geochemistry departments at Berkeley and Lamont Doherty, was not in the same professional universe as a Pemex consultant based in Mexico. The letter that might have closed the gap got lost on an overloaded desk. The single conference paper that might have closed it went unnoticed in an underattended session. For 12 years, the answer existed, and the people who needed it did not know it existed because nothing had yet routed the signal between them. This is a pattern that repeats in less dramatic form across the history of almost every field of science. Information is rarely limited by logic and often limited by attention. The crater at Chicxulub is the textbook case, not because the delay was unusually long, but because the resolution, when it came, was so clean that the whole shape of the problem becomes visible in retrospect. What fixed it in the end was not a new discovery. It was a Houston science reporter who happened to know two people. Byers, as far as I know, never received a scientific credit commensurate with the role he played. He continued working as a journalist, covered other stories, and retired in due course. The standard narrative of the Chicxulub identification names Alvarez and Hildebrand and Penfield, and these are the right names to name, but a careful telling of how the identification actually happened has to include a reporter in Houston making a phone call. The crater would have been found eventually by some combination of other people looking at other data. The question is only how long later and how much else might have been learned in the meantime if the connection had happened earlier. 12 years is a long time in scientific investigation. It is the interval during which an entire generation of graduate students could have been writing theses on a confirmed crater rather than on a hypothetical one. In the years following the geology paper, the structure at Chicxulub became the most intensively studied impact site on Earth. The 1991 identification was only the beginning. What the crater contained, what it preserved, and what it could tell scientists about the first day of the world after the Cretaceous. All of that would take another quarter of a century to recover, and the recovery would require drilling directly into the peak ring through a kilometer of overlying sediment from a platform anchored to the seafloor offshore of the Yucatán coast. That expedition would not happen until 2016. What it found there would rewrite, in one continuous core of rock, the minute-by-minute stratigraphy of the impact's first 24 hours. But before any of that, and for reasons that by the early 1990s had become harder to sustain, a parallel argument was still in play, in which the extinction had been caused by something else entirely, or at least not primarily by what had hit the Yucatán. That alternative had distinguished advocates, real evidence, and a duration in the debate that outlasted almost everyone's expectations. It is worth taking seriously because the case for it is better than most people who have only heard of the Alvarez hypothesis assume, and because the eventual resolution of the argument, which came only within the last several years, is itself one of the cleaner examples of how science reaches a conclusion when the stakes are high and the evidence is slow. There is a hypothesis first proposed in the middle of the 1980s and defended with real seriousness by credentialed researchers until the present day that the asteroid did not kill the dinosaurs. The hypothesis does not deny that the impact happened. The iridium is too clear, the shocked quartz is too clear, the crater is too clear. The 1991 Hildebrand paper settled too many things at once to be disputed in its essentials. What the alternative hypothesis proposes is something more subtle, that the impact, real as it was not the primary cause of the extinction, or was not the sole cause, or was only the final blow in a cascade already well underway before the rock ever arrived. And the force the alternative credits with most of the killing is not extraterrestrial. It is geological, continental, and slow. It is called the Deccan Traps, and it sits today as an enormous plateau of stacked basalt across the western half of peninsular India. If you have never heard of the Deccan Traps, the scale of them is worth pausing on, because the numbers are the kind that the channel has been anchoring across earlier chapters, and they need the same treatment here. The Deccan Traps cover something on the order of 500,000 square kilometers of modern India, an area about the size of France and Spain combined. The basalt flows, stacked one on top of another in a sequence of individual lava sheets, reach a total thickness of over 2 kilometers at the thickest points. The total volume of lava extruded over the eruptive interval is estimated at somewhere around 1 million cubic kilometers, which is about 100 times the volume of all the lava erupted from all the world's volcanoes in recorded human history combined. These are not ordinary volcanic numbers. A large igneous province of this magnitude is a planetary scale event in its own right, and the Deccan's eruption did not, in geological terms, happen far from the Cretaceous-Paleogene boundary. It happened across it. The timing is what makes the Deccan hypothesis possible and also what makes it difficult to settle. The eruptive history of the Deccan Traps has been reconstructed through high-precision radiometric dating across the last several decades, and what the dates show is that the main eruption pulse began several 100,000 years before the impact, continued across the boundary itself, and extended for several 100,000 years after. The basalt flows are not evenly spaced. They come in pulses, distinct eruptive phases, each lasting tens of thousands of years, separated by quieter intervals. The magma flowed in enormous surges, laying down stacks of flows rapidly, and then paused, and then surged again. The total duration of the eruptive event was something on the order of 700,000 to 1 million years, and the most voluminous pulses appear to have occurred in the interval immediately around the boundary itself. What a flood basalt of this magnitude does to climate is well established in general principle and uncertain in specific detail. Each individual flow, when it reached the surface, released enormous quantities of volcanic gas, sulfur dioxide, carbon dioxide, chlorine, water vapor, trace amounts of other reactive species. The sulfur dioxide, oxidizing in the atmosphere to form sulfate aerosols, would have cooled the climate on timescales of years to decades per pulse, much as an ordinary volcanic eruption does, but on a much larger scale. The carbon dioxide, with a much longer atmospheric lifetime, would have accumulated across multiple pulses and warmed the climate over longer intervals, tens to hundreds of thousands of years. The net effect over the full eruptive history was complex, alternating pulses of cooling from the sulfate aerosols and sustained warming from the accumulating carbon dioxide, producing a late Cretaceous climate that was, by several proxies, already disturbed before the impact arrived. The case made by the Deccan hypothesis, in its strongest form, is that the late Cretaceous biosphere was already under severe and mounting climate stress when the asteroid hit. That species were already in decline, that the ecosystems were fragile and depleted, and that the impact, severe as it was, struck a world that had already been softened for mass extinction by a parallel cataclysm. On this view, a world not already weakened by Deccan volcanism would have survived the impact with more of its biota intact. The asteroid killed the dinosaurs in this framing only because the dinosaurs were already half killed. The most tenacious advocate of this view for the last 40 years has been Goethe Keller, a paleontologist at Princeton. Keller's work on the boundary, extending back to the early 1980s, has consistently argued that the marine microfossil record around the boundary does not look like a single instantaneous event, that some extinctions appear to precede the iridium layer by tens of thousands of years, that climate disturbances predate the impact, and that the pattern is better explained by a pre-impact crisis driven by Deccan emissions than by the sudden clean kill the Alvarez hypothesis implies. She has written dozens of papers on this topic across decades, trained students, organized meetings, and maintained the Deccan alternative as a live scientific possibility, even when the broader community treated it as increasingly marginal. The intellectual history of the impact vs volcanism debate is, in substantial measure, also the intellectual history of Keller's career. It would be easy and wrong to caricature her position. The Deccan hypothesis in its most careful form is not a crank theory. It is a minority reading of contested evidence defended with rigor, and in some of its subclaims, it has been supported by other researchers independently. The question of whether the late Cretaceous biosphere was already stressed before the impact is a real question. The question of whether some groups, particularly certain marine microfossil lineages, show decline signatures preceding the boundary is a real question. The question of what Deccan emissions actually did to late Cretaceous climate is a real question, and the answer is not trivial. What has happened over the last decade is that the answers to those questions have begun to converge on a picture in which the Deccan was real and significant, but secondary. In 2020, a team of researchers led by Pincelli Hull at Yale published in Science a careful synthesis of the available paleoclimate and extinction pattern data across the boundary. The study used high-resolution temperature reconstructions from marine sediment cores, compared them with the dating of Deccan eruptive pulses, and evaluated the extinction patterns against both single-cause and multi-cause scenarios. The conclusion was detailed and, in the specific sense that matters, decisive. The Deccan emissions had indeed perturbed late Cretaceous climate. There was a warming episode of 2 to 4 degrees across the late Maastrichtian, and it was plausibly driven by Deccan carbon dioxide. But the warming had ended before the boundary. The climate had returned to something close to its earlier baseline by the time the asteroid arrived. The extinction, when it came, did not strike a biosphere in the middle of a climate crisis. It struck a biosphere that had recently come through a climate perturbation, was recovering from it, and was hit by an event of a completely different magnitude and mechanism. The picture the Hull study and several parallel lines of evidence have converged on, and which now sits as the best current reading of the full Cretaceous-Paleogene boundary, is something like this. The Deccan was significant. It added stress to the late Cretaceous world. It probably contributed to the slow extinctions of certain specific groups, some marine microfossils, some vegetation communities, in the hundreds of thousands of years leading up to the boundary. But those slow pre-impact losses are a small fraction of the full end Cretaceous extinction. The great majority of the extinction, the ammonites, the non-avian dinosaurs, the marine reptiles, the rudest reefs, the calcareous plankton crash, the 75% figure that everyone remembers, happened simultaneously with the impact within the interval resolvable in the rock record, which is on the order of thousands of years at most. The impact did the killing. The Deccan did something, but the something was smaller, earlier, and ecologically distinct. This is worth stating carefully, because it is not the usual shape of a scientific debate resolving itself. The more familiar pattern in a long-running controversy is that one side turns out to be wrong and the other right, with a clean winner and a clean loser. That is not what happened here. What happened is that the two sides both turned out to be correct about parts of the record, and the synthesis that resolves the debate incorporates real evidence from both. The impact hypothesis is correct about what killed most of the extinct species. The Deccan hypothesis is correct about something having been going on in the late Cretaceous climate that was not business as usual. Both mechanisms operated. They operated on different scales, at different intensities, with different ecological consequences, and the extinction pattern we see in the record is the combined signature of both, though with the impact doing the overwhelming majority of the lethal work. Keller, in recent years, has continued to argue for a larger Deccan role than the Hull synthesis assigns. That is an ordinary state of affairs in science. A researcher who has spent 40 years developing a particular interpretation does not typically concede it fully on the basis of one new paper, and the scientific community does not typically expect her to. The case for a very large Deccan role has weakened. The case for zero Deccan role has also weakened, and the community's present position is that both contributed, with the impact as primary and the Deccan as secondary. That is where the evidence now sits. It is also, in an important sense, a better resolution than either of the two competing hypotheses was able to articulate in isolation, because the combined picture explains more of the data than either single cause hypothesis could. If you find yourself, after hearing this, thinking that the truth turned out to be messier than either side wanted, you are right. And you are noticing something that happens fairly often at the resolution of major scientific controversies. Natural processes are rarely caused by one thing. They are usually caused by several things operating together, each with its own contribution, and the task of science is to partition those contributions correctly, rather than to select a single winning cause. The Cretaceous-Paleogene boundary is a textbook case. It had a primary cause and it had a secondary cause, and for about 40 years, different research communities each grasped one of the two causes and held it to the exclusion of the other, until enough evidence accumulated on both sides for the picture to resolve. The resolution in this case also closes off a set of questions that had remained open for decades about what the impact really did on its own, as distinct from what a stressed climate might have been doing in parallel. With the Deccan's role now constrained to a smaller, earlier perturbation, the consequences of the impact itself can be read more cleanly from the record. The 75% extinction figure is the impact's figure. The speed of the marine collapse is the impact's speed. The specific selectivity patterns, the 25 kilogram cutoff, the arboreal losses, the acidification signatures, are all readable as the impact's direct signature without having to subtract an unknown Deccan contribution from each of them. What remained to be seen, after all of this had been pieced together across 40 years by several generations of researchers, was what the crater itself could be made to tell. The 1991 paper had confirmed its location. The chemistry of the boundary clay had confirmed its global reach. The Deccan synthesis had confirmed its primary role. But the crater as a physical object, in its intact first-day form, had never been directly sampled. The rocks of the peak ring had never been brought up. The immediate aftermath of the impact had never been read directly from the stratigraphy of ground zero. That would change in the spring of 2016 on a platform anchored offshore of the Yucatán coast, with a drill string descending through a kilometer of younger sediment to a layer of rock that had last seen daylight on the worst morning in the history of life. The drill string came up through a kilometer of younger sediment and brought with it, in cylindrical segments about 3 meters long each, the rock record of the worst day in the history of vertebrate life. The operation took place in the spring of 2016 from a small platform anchored to the seafloor about 30 kilometers offshore of the Yucatán coast, almost exactly above the buried edge of the peak ring. The platform was not a conventional oil industry drill rig. Those are designed for rapid, high-volume extraction of oil from porous sedimentary reservoirs, and they are not built for the kind of slow, delicate coring that recovers continuous cylinders of rock without breaking them. Instead, the project used a specialized mission-specific platform called the Myrtle, operated by the European Consortium for Ocean Research Drilling. The Myrtle was essentially a large lift boat, a shallow water platform with 3 enormous legs that could be jacked down to the seafloor to provide a stable working surface a few meters above the waves. From that platform, a drill crew could recover core samples with the care the rock required. The expedition was a joint venture of 2 international drilling programs, the International Ocean Discovery Program and the International Continental Scientific Drilling Program, and it was led by 2 principal scientists. Sean Gulick, a marine geophysicist based at the University of Texas at Austin, and Joanna Morgan, a geophysicist at Imperial College London. They had been working toward this drilling campaign, together and separately, for roughly a decade before the platform went in the water. The scientific target was specific and unusual. They were not drilling to recover a stratigraphic sequence of ordinary marine sediments. They were drilling to reach and to sample in continuous core the peak ring of the Chicxulub impact structure itself, the innermost ring of uplifted crystalline rock that had been forced upward in the seconds after impact, before being rapidly buried by the chaotic aftermath. The scientific question about peak rings before this expedition had been genuinely open. Large impact craters on the Moon, on Mercury, and on Mars show peak rings as conspicuous features, and the geophysical theory of how they form had been debated for decades without direct evidence. 2 main hypotheses competed. One proposed that peak rings form by the inward collapse of the transient crater walls, surface rocks sliding down into the crater from its rim. The other proposed that peak rings form by the rebound of deep crustal rocks from beneath the point of impact, forced upward by the pressure release after the compression pulse had passed. These hypotheses predicted very different things about what the peak ring rocks would actually be made of. The first predicted that the peak ring should contain Mesozoic sedimentary rocks, limestones, anhydrites, derived from the surface materials around the crater rim. The second predicted that the peak ring should contain Precambrian basement granite, rocks that had originated 10 kilometers or more below the surface and been forced up through the collapsing structure of the crater in the minutes after impact. The core settled the argument. What came up across the target interval of roughly 600 meters of continuous recovery was granite, fractured, shocked, thermally altered granite, unmistakably Precambrian crystalline basement, lifted from deep below the surface and now sitting at the top of a buried ring 140 kilometers across. The rebound hypothesis was correct. Peak rings form when deep rocks are violently uplifted by pressure release after a very large impact, and the Chicxulub peak ring is made of the basement of what was, 66 million years ago, a stable continental shelf. That shelf was briefly turned inside out. The innermost rocks were lifted toward the sky and then buried under the cascade of material collapsing back into the crater. The sequence of events had been completed in a matter of minutes. The rock record of those minutes had sat intact for the next 66 million years, and in 2016, a team of scientists finally brought it up. But the granite was not, by itself, the most important thing the core contained. Above the peak ring granite, the core recovered approximately 130 meters of a complex chaotic deposit that captured, in continuous stratigraphic order, the first 24 hours after the impact. The scientific team, led in the detailed stratigraphic work by Gulick and a large group of co-investigators, published their analysis in 2019 in a paper in the Proceedings of the National Academy of Sciences under a title that did not overstate its subject, The First Day of the Cenozoic. What they had recovered, in 130 meters of rock, was an hour-by-hour record of what had happened at the impact site in the period between the arrival of the asteroid and the settling of the first post-impact ocean sediments. The stratigraphy, read from the bottom up, tells a story that can almost be narrated minute by minute. At the very bottom, immediately above the impact-shocked granite, lies a thick unit of impact melt rock. Rock that had been liquefied by the impact, cooled in place, and solidified as a glassy and partly crystalline mass. This material represents the first minutes to tens of minutes after the collision, as the crater floor was still molten and beginning to cool. Above the melt rock lies a thick layer of suevite, a breccia composed of fragments of various target rocks, impact melt clasts, and shocked mineral grains mixed chaotically together. The suevite was deposited as the collapsing crater walls, and the redeposited ejecta settled back into the basin of the newly formed crater in an interval that probably lasted minutes to a few hours after the initial contact. Above the suevite, the core shows a thin layer of finer-grained material that appears to have been sorted by flowing water, the signature of the ocean rushing back into the crater after the initial impact cavity had formed. This would have happened within perhaps an hour or two of the impact, as the temporary displacement of seawater around the impact site collapsed back, flooding the crater from the open ocean to the north. Above that water-sorted layer, more finely sorted sediment deposited as the turbulent flow slowed. And at the very top of the first-day deposit, a thin layer of settled material containing charcoal, woody organic debris, and fine particulate matter. The signature, interpreted by the team, of a tsunami wave returning to the crater after reflecting off distant shorelines and carrying with it the burnt remains of coastal forests from whatever shorelines had been closest to the impact. 130 meters of rock, 24 hours of deposition, a rate of sedimentation roughly 10 million times the rate at which ordinary ocean sediments accumulate. What the stratigraphy told the team, read as a continuous record, was everything the models had predicted, confirmed in physical sediment that had been in place for 2/3 of 100 million years. The impact melt deposited in minutes, the suevite deposited in hours, the reflooding of the crater by seawater in the first couple of hours, the returning tsunami within the first day, the charcoal in the tsunami deposit, indicating that forests around the Gulf of Mexico had burned within the time it took a tsunami wave to cross the Gulf and return. The sequence of events that had been reconstructed from a combination of physics modeling, global boundary clay chemistry, and fossil evidence was confirmed in direct stratigraphic order by the rocks of the crater itself. There was, however, one significant thing the core did not contain. The target rocks at the Chicxulub impact site before the event had included a substantial thickness of anhydrite, calcium sulfate, forming part of the late Cretaceous evaporate sequence of the Yucatán platform. Anhydrite is a common sedimentary mineral, and the stratigraphic sequence around the crater, as reconstructed from neighboring drill holes outside the peak ring, contains significant quantities of it. If the peak ring had been formed by the collapse of surface rocks, if the Mesozoic sedimentary hypothesis for peak ring formation had been correct, then the core should have contained anhydrite fragments, perhaps in substantial quantity. It did not. Not only was the peak ring made of granite rather than sedimentary rock, but the anhydrite that had been present at the impact site before the collision was essentially absent from the recovered material. This absence is itself evidence, and it is one of the more elegant kinds of evidence in the study of the impact's climate effects, because it tells you what happened to a set of rocks, not by finding them, but by finding that they were no longer there to be found. The anhydrite, the team concluded, had been preferentially vaporized. When the asteroid struck, the anhydrite at the impact site had been turned, along with the other surface rocks, into vapor. Unlike the granite, which was partly liquefied and partly fragmented, but largely retained as impact melt and breccia at the site, the anhydrite was so thoroughly vaporized that almost none of it was recaptured as the crater reformed. Its atoms, the calcium, the sulfur, the oxygen, went up into the plume, into the stratosphere, and into the long, slow chemistry of the impact winter. The missing anhydrite is the missing sulfur, and the missing sulfur is what, having reached the stratosphere, formed the aerosols that contributed to the global darkening and cooling across the years after the impact. You can stand today in a climate-controlled core repository in Bremen, Germany, where the Chicxulub cores are archived, and look at the rock that came up through the drill string in 2016. You can see the melt rock, you can see the suevite, you can see the sorting patterns in the finer deposits at the top. You can see, if you know what you are looking for, the specific places in the sequence where specific minutes of the first day are preserved. And you can note, by what is not there, the missing anhydrite, whose absence is in its own way the most consequential finding of the whole expedition, because the anhydrite's absence at the site is the anhydrite's presence in the climate, and the anhydrite in the climate is a substantial fraction of why the extinction was an extinction rather than a merely large disturbance. What the core did, in effect, was convert the entire cascade, from impact to extinction to recovery, into something that could be held. Before 2016, the cascade was a reconstruction built from many separate lines of evidence, each collected in different places, each carrying its own uncertainties, fitted together by inference across the global boundary layer. After 2016, one continuous column of rock recovered from ground zero preserved most of the key beats of the cascade in their original stratigraphic order. The inference still held, but now it had a physical spine. The inquiry that had begun in a limestone gorge in Umbria in the 1970s had been extended through 4 decades of field and laboratory work across every continent and had resolved its longest-running internal debate only within the last several years, now had at its centre a cylindrical rock core in a German warehouse. The scientific question that had started the whole sequence: what is this thin layer of clay, and how long did it take to form, had, across the work of hundreds of scientists over 50 years, produced an answer detailed enough to be read minute by minute from the rocks of the crater itself. What the answer showed was not that the impact had killed the Cretaceous world. That had been established by 1980. It showed, rather, exactly how it had done so. The mechanism in all its stages, the vapor plume, the re-entering ejector, the thermal pulse, the ocean flooding back into the crater, the tsunami reflecting from distant shores, the forests burning within the first day, the sulfur lifting into the stratosphere, the darkening, the cooling, the acid, the silence, the selectivity, the recovery. All of it, by 2020, could be read forward from first principles and confirmed against the physical record at every step, which leaves, for the final part of the story, only the question of what that record now means for the world that comes after, for the planet as it currently is, with its single species capable of understanding its own geological past, and with the first capability in 4.5 billion years of Earth history to do something about an asteroid seen approaching from a distance. For 4.5 billion years, the planet took its impacts without any capacity to respond to them. This is not a statement about the impacts. It is a statement about the planet. Earth has been struck by objects of every size across its history, from micrometeorites that arrive daily and dissolve harmlessly into the upper atmosphere, to asteroids of the Chicxulub scale that arrive on intervals of tens to hundreds of millions of years and do not dissolve into anything. In between, there is a continuous distribution. Objects about 1 kilometer across arrive every few 100,000 years on average. Objects about 100 meters across arrive every few thousand. Objects of 10 meters are seen in the sky once a year or so and usually burn up before they reach the ground. The larger ones do not burn up. The planet absorbs them, adjusts to them, and across timescales of millions of years reshapes whatever they have altered. None of this absorption, at any point in those 4.5 billion years, was accompanied by any element of choice. The small thing that changed, in a way that is easy to miss if you do not look for it, happened in the second half of the 20th century. It is easy to miss because it was not a single moment and had no fanfare. It happened gradually as astronomers with increasingly sensitive telescopes began to catalogue small bodies in the solar system and pay attention to their orbits. In the 1950s and 60s, a handful of asteroids were known that crossed Earth's orbit. By the 1980s, a few hundred. In the 1990s, the United States Congress directed NASA to search systematically for objects that could pose an impact risk. And by the early 2000s, dedicated survey telescopes were operating continuously. Today, the catalogue of known near-Earth objects exceeds 30,000, and essentially all of the larger ones, the kilometre-scale bodies whose impacts would produce global consequences, have been found and tracked. None of them, as of the time of this recording, is on a trajectory that threatens the Earth in any foreseeable interval. The catalogue is, in that sense, quietly reassuring. The smaller bodies are a different story. Objects a few hundred meters across, capable of producing regional rather than global catastrophes, are numerous, estimated somewhere around 25,000 in total within Earth-crossing orbits. And the catalogue of them is incomplete. Maybe half of them have been found. The rest are still out there, on orbits we have not yet mapped, most of them not threats on any reasonable timescale, some of them potentially someday. Below a few tens of meters, the population is essentially impossible to catalogue in advance, and the ones small enough to produce only local damage, of the kind that flattened forest near Tunguska in 1908, or the one that exploded over Chelyabinsk in February of 2013 and injured over 1,000 people through broken glass, continue to arrive occasionally without warning. What would happen if one of the larger ones were detected on a trajectory that did threaten Earth was, until recently, an entirely theoretical question. The theoretical answer was that several deflection methods might work in principle. You could, if you had enough advance warning, put a heavy spacecraft next to the object and let its mutual gravitation slowly pull the object off course. You could, with less elegance and more force, detonate a nuclear device near the object's surface to vaporize part of it and produce a reaction thrust that moved what remained. Or you could do the most straightforward thing, which is also the crudest. You could run a spacecraft directly into the object at high speed and transfer the spacecraft's momentum into the object, nudging its orbit. The last of these, the kinetic impactor method, required no new physics and no exotic technology. It required aiming accurately and hitting hard. It was, in engineering terms, within reach. No one had ever tried it. On September 26, 2022, at 7:14 p.m. Eastern Time, a small NASA spacecraft called the Double Asteroid Redirection Test, known as DART, arrived at its target. The target had been selected carefully. It was a small body named Dimorphos, about 160 meters across, roughly the size of a sports stadium, which orbited a larger body called Didymos, about 800 meters across, in a binary asteroid system roughly 11 million kilometers from Earth at the moment of impact. Neither Dimorphos nor Didymos posed any threat to Earth. They had been selected precisely because they did not. A full-scale test of a deflection technology is not the kind of thing you want to try on something that might actually hit you. The Dimorphos-Didymos system was chosen because its binary structure made the deflection measurable. The small body's orbit around the larger body before the impact took 11 hours and 55 minutes. Any change to that orbital period after the kinetic impactor struck could be measured precisely by telescopes on Earth, giving a direct quantification of how much momentum the impact had transferred. DART itself was about the size of a vending machine, weighing roughly half a ton at the moment of impact. It had been launched from California in November of 2021 on a trajectory that carried it to Dimorphos across 10 months of flight. For the final 4 hours of its approach, the spacecraft flew autonomously, guided by its own optical sensors tracking the target. The final images streamed back to Earth, transmitted at the speed of light across 11 million kilometers with a one-way travel time of about 37 seconds, showed Dimorphos growing larger and larger in the spacecraft's camera. Individual boulders on the asteroid's surface became visible. The texture of the rubble pile surface came into focus. The last complete image, transmitted moments before the final one, showed a field of fractured rock filling the frame. Then the transmission ended because the spacecraft no longer existed. On the ground, about 1 million people were watching the live stream. Some of them were scientists and engineers at the Johns Hopkins Applied Physics Laboratory, which had built and flown the spacecraft. Some of them were NASA staff following a technology demonstration that represented a decade of program development. Most of them were ordinary people who had tuned into a broadcast on the internet because the event was worth watching. What they were watching, whether the broadcasters framed it this way or not, was the first time a species anywhere on Earth had intentionally altered the motion of a body in the solar system. The result, when the orbital measurements came in over the following days and weeks, was better than the mission's success criterion by a substantial margin. The orbital period of Dimorphos around Didymos had been shortened by about 32 minutes. The mission had specified a minimum success of 73 seconds of change. The actual change was roughly 25 times larger than the minimum. Part of the reason for this unexpectedly large effect was that the debris ejected from Dimorphos by the impact had itself carried momentum away from the asteroid, producing a recoil effect in addition to the direct momentum transfer from the spacecraft. The kinetic impactor method, when tested at full scale for the first time, had worked better than its designers had predicted. The result was quietly announced. NASA held a press conference. Papers were published in the scientific journals over the following year, detailing the mechanical analysis and the momentum transfer efficiency. A follow-up mission from the European Space Agency called HERA was dispatched to the Didymos-Dimorphos system to study the post-impact state of Dimorphos directly and characterize the crater that DART had made. HERA was launched in October of 2024 and will reach the target in late 2026. There was no ticker-tape parade. The news cycle was short. Within a few weeks, most of the general public had forgotten the event. This is probably appropriate. The demonstration was a scientific and engineering milestone, not a moment of civilizational import, and the sober framing in which it was reported, one test, one target, specific numerical results, ongoing further research, is a more accurate register than the alternative would have been. But it is worth pausing briefly to register what had actually happened. For the entire history of life on Earth, which is to say for approximately 4 billion years, every asteroid that struck the planet struck without opposition. The Cretaceous impact, 66 million years ago, was neither prevented nor anticipated, nor was any previous impact, nor was any subsequent one. The planet absorbed what arrived, and the organisms on the planet either survived the absorption or did not. There was no mechanism by which the direction of travel of an incoming object could be changed. There was no mechanism by which an object could be detected in advance and made the subject of deliberate response. These are capabilities that life on Earth simply did not have. Within your lifetime, and probably within your listening to this recording, that changed. You are alive in the first generation of any species on this planet that has pushed back against an object in space, that has applied, in a controlled and measurable way, a force of its own to a celestial body and altered the body's trajectory. The change DART made to Dimorphos was small. Dimorphos is small. The test case was a demonstration rather than an operational response to a threat. But the capability is now demonstrated. The physics has been shown to be tractable. The engineering has been shown to work. The capacity has moved from theoretical to actual. This is not a reason to relax, and it is not a reason to panic. The catalogue of large near-Earth objects is essentially complete, and none of the known ones are threats. The catalogue of middle-sized objects is incomplete, and a hypothetical discovery of a threatening one, tomorrow or in 20 years, would be the beginning of a very different kind of scientific and political response than the DART mission was. A real deflection against a real threat would require far more advanced warning, far larger spacecraft, or far more sophisticated methods than a single half-ton vending machine-sized impactor arriving one time. The DART test did not prove that the Earth is safe from impacts. It proved that the species on the Earth now has, for the first time, the beginnings of a capability for responding to one. What that capability means, ethically and strategically, is a question that will be worked out in the coming decades by people whose professional job it is to think about these things. The planet-scale calculation, meanwhile, remains what it was. Impacts of the Chicxulub scale arrive on timescales of tens to hundreds of millions of years. The current interval since the last one is shorter than the average interval between them, which means the next one is statistically more likely to arrive sooner than later, in a probabilistic sense. It is also statistically likely to arrive far, far later than any living human will be around to see. The numbers do not tell anyone anything useful about whether they should, personally, be concerned. What the numbers tell you, if anything, is that the planet's timescales are long, and that the generations alive during the narrow interval when the species first acquires the capacity to reshape its own extinction risks are in an unusual position relative to every prior generation of living things on Earth. Your ancestor in the burrow in Colorado could not have pushed back against the sky. None of its descendants for 66 million years could have pushed back against the sky. You, in a different sense of the word, can. Whether that matters at any relevant scale of human life, whether it will ever be used, whether it will ever be needed, is not something anyone currently knows. What it is, unambiguously, is new. In a 4.5 billion year biography, it is a capability that has existed for less than a decade. The rest of the story the channel has been telling across these hours has been about what the planet did without us. What it survived, what it rebuilt, what it eventually produced. The part that comes after this, the part that is still being written, is about a planet that has now, in one small, specific way, started to be accompanied in its own biography by something that can read it. What the science can now say, after 50 years of investigation across every continent and into a kilometer of rock beneath the Yucatán shelf, is this. On a morning in the northern hemisphere spring, approximately 66,043,000 years ago, a chondritic asteroid about 10 kilometers in diameter arrived from the northeast at an angle of between 45 and 60 degrees above the horizon and struck the shallow carbonate platform of the late Cretaceous Yucatán. The energy released was on the order of 10 to the 23rd joules, equivalent to something like 10 billion simultaneous Hiroshima bombs, or 100 million detonations of the largest thermonuclear device ever tested by human hands. The impact crater formed within minutes, transient and then modified, leaving a structure 180 kilometers across and extending down through the sedimentary platform and into the Precambrian basement beneath. The peak ring, formed by deep crustal rebound, was uplifted and rapidly buried under the chaos of the reforming crater. Within the first 24 hours, the following happened, in order. A plume of vaporized seafloor and impactor rose above the atmosphere, carrying with it thousands of gigatons of ejecta, a substantial fraction of which would distribute globally. The thermal pulse from re-entering spherules reached the surface across the planet within hours, with peak radiative flux of something like 5 to 15 kilowatts per square meter, sustained for a few minutes, sufficient to ignite widespread, if not necessarily perfectly global fires. The ocean flooded back into the crater within the first hour, and by the end of the first day, a tsunami that had reflected off distant shorelines had returned to the crater carrying the charcoal of whatever had burned. 130 meters of rock accumulated on the crater floor in those 24 hours, preserving each of these stages in continuous stratigraphic order and sat undisturbed until the drilling of 2016. Over the following years to decades, the fine silicate dust and sulfate aerosols lofted into the stratosphere produced a global darkening sufficient to reduce solar transmission by something like 80% for the first year and by at least 50% for 9 years after that. The darkening shut down photosynthesis in most of the surface ocean and crippled it across most of the continents. The impact winter, extending the initial cooling of the sulfate phase into the longer-lasting cooling of the dust phase, held global temperatures substantially below their pre-impact values for the better part of a decade and a half. Acid rain driven by the oxidation of the sulfur released from vaporized anhydrite combined with carbonic acid from the carbon dioxide of vaporized carbonate to drop surface ocean pH by approximately 1/4 of a unit in a geologically instantaneous interval. An acidification event roughly 10 to 100 times faster and 2 to 3 times larger in magnitude than what the modern ocean is currently undergoing. The biological consequences were severe and selective. Approximately 75% of species on Earth at the time did not survive the boundary interval. Every non-avian dinosaur lineage ended. Every pterosaur ended. The ammonites, a 300 million year lineage that had survived every previous mass extinction, ended, the specific mechanism being the failure of their planktotrophic larvae to find food in the acidified and darkened surface ocean. The large marine reptiles, mosasaurs, plesiosaurs, the elasmosaurs, ended. The rudest bivalves that had built the tropical reefs ended. The calcareous nanoplankton crashed from roughly 100 species to fewer than 10. The planktonic foraminifera were reduced, for some hundreds of thousands of years after the boundary, to effectively a single surviving lineage. Across the terrestrial realm, the body size cutoff for survival was somewhere around 25 kilograms, and the habitat cutoff was the presence or absence of closed canopy forest, which collapsed globally and took millions of years to rebuild. The arboreal specialists were removed, across mammals and birds alike, and the non-arboreal ground dwellers that survived became the seed populations from which every modern terrestrial vertebrate lineage that exists today was eventually rebuilt. What the science cannot say, or cannot say with full confidence, is a somewhat smaller set of things. The exact degree of global uniformity in the wildfires remains debated. The precise magnitude of the Deccan Traps contribution, though now constrained to a secondary role, retains some quantitative uncertainty. The specific temperatures reached at specific latitudes during the impact winter are known in their broad shape and not in their detailed profile. The question of whether any non-avian dinosaur lineage persisted in local refugia for thousands of years after the boundary, rather than dying effectively at the boundary itself, is not fully closed by the current evidence. The rate at which the ocean chemistry recovered and the ecological specifics of the strangelove to living ocean transition are known in general outline and in some local detail, and they will become better known over the coming decades as more high-resolution records are analysed. These are questions of refinement rather than of direction. The shape of the cascade, from trigger to recovery, is settled. What the science absolutely cannot say is anything about meaning. There is no scientific answer to the question of what it was like for the animals living through the event to live through it. There is no scientific answer to the question of whether the event should be thought of as a tragedy or as a phase of the planet's normal operation, or as a reset, or as an injustice, or as luck. These are human questions about a non-human process, and the process does not contain within itself the framework for answering them. It simply happened. What did happen afterward, in the long, slow interval that followed, is worth tracing briefly. For the first 100,000 years after the impact, the terrestrial biosphere in most of the world was in a state paleontologists sometimes call a disaster ecology. Low-diversity ecosystems dominated by a handful of opportunistic species, with the fern spike visible in sediments at many sites as the clearest botanical signature of the interval. In the oceans, the strangelove phase gave way to the living ocean phase over the first hundreds to thousands of years, and the biological pump resumed operation in a degraded form that persisted for tens of thousands of years more. Between roughly 100,000 and 300,000 years after the impact, in the best-studied sections of the terrestrial record, in the Coral Bluffs fossil-rich sequence in what is now Colorado, for example, ecosystems began to rebuild with increasing complexity. Mammals diversified into niches that had been closed to them for 150 million years. New plant communities emerged. Large-bodied mammals appeared within the first million years. By 300,000 years after the impact, local ecosystems had returned to something approaching functional equilibrium, although with entirely different cast members than before the event. The deeper recovery, by which is meant the return of morphological diversity and ecological complexity comparable to what had existed in the late Cretaceous, took much longer. Marine morphological disparity in planktonic foraminifera did not return to pre-impact levels for something between 5 and 10 million years. The full diversification of modern mammalian orders played out across roughly the first 10 to 15 million years of the Cenozoic. Coral reefs, devastated by the loss of the rudest bivalves, did not return to structural complexity comparable to the late Cretaceous reefs for tens of millions of years, and when they did, the reef builders were different organisms than before. The scleractinian corals, which had been minor players in the Cretaceous, inheriting a world in which their former competitors no longer existed. Across all of this, the thread ran forward. The small mammal in the Colorado burrow, the small bird on a post-impact shoreline, the small reptile in a freshwater pond, the small fish in the surviving portion of a planktonic lineage, these and 10,000 other small continuing lines of organisms persisted, reproduced, and became slowly the cast members of a new world. That world's complexity was not a restoration. It was a rebuilding from fragments. The specific species, ecosystems, and body plans that had been lost did not return. What returned over millions of years was the general capacity of the biosphere to support diverse, structured, interconnected life. The filling of that capacity with specific forms, whales, bats, primates, elephants, horses, and eventually the nervous system that is listening to this voice, was the work of the Cenozoic, and it was work the planet performed at its own pace, on its own schedule, independently of any individual organism's sense of how long it was taking. Here, near the end, the channel's ground rises into the foreground for what will be a brief interval and then fall away again. The thing that is easiest to lose in an account like this one is the ordinariness of the event for the planet itself. The impact was an enormous catastrophe for the life on Earth at the time. It was one more event among many for the Earth as a material object. Over its full biography, the planet has survived glaciations that covered most of its surface in ice, oxygenation events that poisoned most of the then existing microbial biosphere, supervolcanic eruptions that darkened the sky for years, asteroid impacts smaller and larger than Chicxulub, tectonic rearrangements that moved entire continental masses across latitudes, and several earlier mass extinctions more severe than the one the impact caused. Each of these events was, for the life of its time, the worst thing that had ever happened. Each of them was, for the planet, one phase of an ongoing process. The planet is, in ways that are difficult to hold on a human scale, enormously patient. The patience is not wisdom, and it is not virtue. It is the simple fact that geological time is longer than ecological time, and ecological time is longer than biological time, and biological time is longer than the lifespan of any individual organism, and all of these are longer than the interval across which any single animal, including any human, can experience its own life. The planet is not patient because it has chosen to be. It is patient because the clocks it runs on are slower than the clocks anything alive runs on, and everything alive encounters it at scales the planet itself does not register. This does not mean the events do not matter. They matter enormously to the organisms they happen to. The end Cretaceous event mattered to every ammonite that failed to produce viable larvae, to every small mammal that either did or did not survive its winter, to every lineage that crossed or did not cross the boundary. The mattering is real and ongoing. What the planet's patience adds to it is a frame, the fact that the mattering, however intense, is happening inside an interval longer than the mattering, and that the interval continues after the mattering stops. Your own life is being lived inside that interval. The worst thing that ever happened to life on Earth, in terms of the fraction of species lost, was not the Chicxulub impact, but the end Permian event, about 186 million years earlier, in which approximately 95% of marine species disappeared. The second worst was the end Ordovician event, about 444 million years ago, in which perhaps 86% of species disappeared. The third worst was the late Devonian crisis, in which extinctions played out in several pulses across 15 to 25 million years. The fourth worst was the end Triassic event, about 201 million years ago, which ended a different great lineage of reptiles and opened the way for the dinosaurs. The fifth worst was the end Cretaceous event, the subject of this recording. The planet survived all of them. Each time something small was not quite killed, each of those small somethings became ancestor to what came next. You are descended from the survivors of every one of those 5 events, because the line that leads to you had to cross every one of those boundaries, and did, not by design, not by virtue, not by anything other than the continuation of a thin thread across extraordinary spans of time. The thread was never guaranteed. At every point it could have broken, it did not. And so here you are, in whatever room you are listening in, attached by an unbroken chain of living cells to an animal that slept through a bad winter in Colorado 66 million years ago, and through deeper chains to animals that slept through winters in the Permian and the Triassic and the Devonian and the Cambrian before that, and to small forms in the earlier oceans that survived the first great oxygenation, and ultimately to something very old and very small in waters we can no longer directly see. That thread is the fact the planet's patience protects, not the individual organism, which the patience does not protect at all, not the species, which the patience is indifferent to. The thread, the fact of continued life across the intervals during which most of the forms of life at any given moment are being replaced by other forms. There is not much more that a documentary like this can add at this point, beyond the quiet observation of what has been traced. The morning was ordinary. The rock arrived at 9 minutes before noon, from a direction no one had been watching. The sky caught fire for a small interval of a specific afternoon. The darkening followed, and the cold and the acid and the silence. The forests fell, the oceans thinned, the large animals died in ways slow enough that most individuals never understood what was happening to them. The small animals waited. The survivors carried forward. The crater sits still, a kilometer beneath the modern seafloor, and it will sit there for some tens of millions of years longer as the slow burial continues and the continental margin evolves. The iridium in the global clay layer will remain in place for as long as the rocks containing it remain above subduction zones, which for most of them will be millions of years more. The record of what happened is stable. Everything else is alive and moving, and will continue to move until it stops.